Hello, 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 hello.
One, two, three, 1, 2, 3. It's, yeah. Do you have to turn it on? Does the red light need to be on here? There's a like button here. It's off, yeah. Oh my. So sure. Okay, that's very loud. Yes, test 1, 2, 3, 1, 2, 3, and yes, it's always. Can is it? It's not. Is it? Okay, it's okay. There's something. Okay, cool. I guess people maybe speak louder than me.
Hello. Oh, nice. Good.
Check, check. Check, check. Okay.
Hi, good morning everyone, and welcome to the 70th SCM Plan workshop on virtual machines and intermediate languages. I'm Yusuke, one of the organizers this year. It's great pleasure to see so many of you joining us here in Singapore, both on-site and online. VMIL has always been a place to share ideas about virtual machines, language implementations, and runtime systems. This year, we have an exciting program featuring one keynote speaker, a 7 paper presentation, and one talk. I'd like to thank our program committee for their thoughtful reviews, the VMIL organizers for their help, and all the authors and attendees who make this event possible. Please enjoy the discussions and don't hesitate to ask questions or reach out during breaks. And I have one small announcement. So this is a tip for presenters. When projecting onto the screen during presentations, please ensure that any special tone settings on your PC are turned off. For details, please refer to the link above. With that, let's begin our first session.
Am I on now? What about now? Ooh. Testing. Oh, okay. I'm on. I just maybe wasn't speaking close enough. Okay. Good morning, everyone. Welcome to the first session of VMIL. My name's Stephen Kell from King's College London. I'll be chairing this session. We have three talks, okay. And the first is Mate from Charles University talking about copy and patch compilation for R. Take it away, Mate.
Okay, thank you. Hi, my name is Mate, and I will be talking about the copy and patch JIT compilation for R. So to start off, let me tell you why I'm here. If you've been at this track last year, you have seen a keynote from Brent Booker on CPython's runtime. One of the major things he talked about was implementing a copy and patch JIT compiler for Python. This inspired the topic of my thesis, in which I implemented the same method of JIT compilation for the R programming language. What I want to show you today is an experience report on how the copy and patch works in the context of R. For those that are not familiar with R, it is a programming language used by statisticians and is mainly designed for intuitive use, even for people from outside of computer science. It is interpreted, dynamically typed, and generally supports a lot of high-level concepts, notably, for example, the read-write access to the call stack via extensive reflection. While powerful, these language features also make it quite slow. And not just slower than C, what I mean is much slower than Python, kind of slow. This also makes it hard to optimize and compile to native code. Now a quick refresher about the copy and patch itself. It is a method for constructing baseline JITs, with its main features being very fast compilation and minimal work for both development and maintenance compared to full-type JIT compilers. It was introduced by Horan Shu at Uppsala 2021, and Horan implemented it for Lua, and he was later followed by Brent, who implemented it for Python, and his contribution is now part of the official CPython distribution. Let's see a quick demo of how copy and patch works. Assume we have a simple toy language and the following statement that you see. Let's also say that this language can be compiled to a stack-based bytecode, as such. To run this bytecode, we create a simple interpreter loop. The semantics of the bytecode are straightforward. The ldcons pushes a compile time constant to stack. The add instruction pops two values from the stack and pushes back the result, and the return instruction pops a value from the stack and returns it from the function. But now comes the core idea for building a JIT using the copy and patch approach. Filtering out the interpreter stuff, we are left with the meat of the instructions. Now we can wrap each of these chunks of code into individual functions. Later, we want to chain these together by returning with a call to the next one, but as we don't know which one will be right now, we put a placeholder in its stead. So the last thing we need to change here is to make these instructions truly standalone, is to also make it a constant in the ldconst stencil a placeholder, like so. These placeholders are designed as external global variables and external functions. Now that we have these standalone instructions, we can run an optimizing ahead-of-time compiler, which emits native code for each function. It is not important to understand the machine code here, but it's important to notice the compiled placeholders, which you can see highlighted in the output. In the context of copy and patch, these are called holes, and they will later be patched with actual data. Now, however, since the returning calls were optimized using take call optimization to simple jumps, we can remove them altogether, leaving us with just the logic of the functions themselves. These chunks of code are then exported into header file, noting the locations of holes in them to later be patched. Combining all of this together gives us something that we call a stencil library. This will be used in the copy and patch run and will be loaded at runtime. And now let's see how the actual run of the copy and patch happens during the runtime. All of what we've seen so far been at the compile time, but now see the runtime itself. So again, we have the same statement, and we first compile it with the bytecode compiler, the same as before. Now the stencil library is loaded into memory, and the copy and patch proceeds. So the first thing it does, it iterates over these instructions. And each time that it finds instruction from the stencil library, it emits the executable code into the memory where it wants to JIT it into. After this is extracted and emitted, we want to specialize this for the constant that is here. So instead of the placeholder, we can now fill in the actual constant, and in this way make this instruction really do what we want to do. After the first operation, we also continue with the second one, which is very similar to the first one, with the only difference that this time we patch the value 2 instead of 1. Since these instructions run sequentially and the first one falls through to the second one, this actually starts to create an executable code that can work as a function, which we'll later see. So we continue in the same way to emit the code for the add instruction. This doesn't have any placeholders to replace any holes, and now we continue on to return, which again is simpler. So now that we have this, we actually, in memory, we actually can call this as a sort of function if we cast a pointer to it. And first we need to mark the memory executable, but after that, this can be called as a regular function, and it returns with the last instruction as such. Now, after showing how the copy and patch works as an idea, let's see how it can be used in R. What you now see is the ldconst instruction from the toy language. But with a few modifications, we get the real ldconst instructions from the R bytecode. To achieve this, we had to extract the implementation of the instruction from GNU-R. This was not as trivial as in the toy language, because GNU-R's bytecode implementation is tightly coupled with its runtime, so we sometimes had to do some modifications to make the instructions standalone. Here you can see our pipeline. So at build time, we extracted the standalone instructions, and at build time, we generate the stencils from them, as you've seen on the toy language, similar to that. We are left with a stencil library, and now to jump to runtime. So when we want to compile our function, it's compiled to bytecode using GNU-R, and then using the bytecode and the stencil library, we use the copy and patch, as we've seen, to emit native code. Here you can see a list of some optimizations that we did. I'll focus on the last three, which might be the most interesting from a technical standpoint. First, let's discuss the specialization of the LD const stencil. Since the R language is dynamically typed, the constant can be of any type, and the implementation has to decide during runtime which to load, right? Well, actually not really. Since the constant is fully known at compile time, we also know its type. So the dynamic dispatch is completely unnecessary. It slows down the execution and bloats memory. To solve this, we can create stencils specifically for each dynamic type. By extracting the code for each of the class cases, we can create much smaller functions without the dynamic dispatch overhead. During the run of the copy and patch, we can choose which to use because we know what is the type of the used constant. Such optimization could be done even in an ahead-of-time compiler. But now let's move to similar optimizations, but one that actually utilizes the power of JIT compilation by using self-modifying code. The for loop in R is then using 3 instructions. Start for, which prepares the frame on the stack. Step for, which advances the iterator, and end for, clearing up the frame on the stack. On the right here, you can see an example R code and the bytecode that it compiles into. The LD const first loads the constant to be iterated over on the stack, and the start for instruction initializes with it. Each iteration, the step for is called, and if the loop is not terminated, it jumps back to its body. After the terminating condition occurs, it just falls through to end the loop. So in these optimizations, we focused on the step for instruction. Same as the LD const, even this instruction suffers from runtime type dispatch, and we can see here that this piece of code is how large the step for implementation is in the GNU R. It is made almost entirely from a single switch statement that chooses one of 10 possible variants to execute. This makes for the step for stencil to be unnecessarily large, suffering again from dynamic type dispatch. And since the value is iterated over, it is known during start for, and this is again unnecessary. What's worse, it applies to each iteration of potentially millions of cycles. But this time, it cannot be solved by just choosing the right stencil at compile time, as it is yet unknown what will be on the stack at that point. We solve this again by extracting the individual variants into separate stencils, each the size it needs. But instead of at compile time, it is at runtime that the code is copied into place, self-modifying to fit the correct dynamic type. More specifically, the modification happens during the start for instruction, where it knows which type it should choose. Let's see a demo of this. So at compile time, during the copy and patch, native code like this is emitted into memory. The space in between start and end for is left blank in the size of the largest step 4 variant. Now let's see the execution. So when the start for begins executing, it actually checks which of the types is there in the iterating variable, and it emits the right stencil into this code inside this memory that was left blank. After this, it also creates the jump from the step 4 until to the end 4, so that it jumps over the space that was also left blank. And after this, it continues, and it continues onto the execution of the step 4 itself, which now doesn't have the dynamic dispatch, and it just uses what needed for this actual type that we need. It iterates over and over until it is finished, and after that, it jumps at the end to end the for loop altogether. So to conclude this, all iterations of the loop use faster, specialized step 4 that we just showed. This makes for a better performance, especially in tight loop benchmarks. Such benchmarks showed 6% average improvement using this operation. Now, to talk about the last discussed optimizations, we must first address how relocations addressing works. Relocations are crucial for the copy and patch. This is the method used to create holes in the stencils. So relocations on x86-64 can be, for our use case, simplified to 3 types. Absolute, which contain a full 64-bit address to the variable that we want to relocate. relative to global offset table, which is now a 32-bit offset from the program counter to a lookup table where the address to the variable is stored, and a relative addressing, which is the relative offset from the program counter directly to the variable. Now, the relative addressing produces the most efficient instructions from these, but the problem with it is, of course, the memory offset has to fit in the 4-byte, 32-bit signed integer range. The problem we face is that we have to choose just one memory model to generate all of our stencils. It is possible that most of the relocations would fit in the fastest relative method, but there will be some that won't, preventing us from using it in general. Yes? It's both smaller and faster to execute because it allows us to use more complex instructions on x86, 64, which directly can address this. Okay. All right, so to solve this, we use a clever trick inspired by the CPython implementation that also tackled with this. The indirect relative method is chosen to compile the stencils. The instructions to access these relocations have 6 bytes, which is 2 for the instruction itself and 4 for the address. During the compilation phase of copy and patch, we detect whether a relocation is near enough in memory in a way it could potentially use the direct relative relocation. If so, we modify the native code. Since such instructions have 5 bytes, they fit inside the 6-byte space that was created by the compiler and can be directly replaced, with the last byte being replaced by a no-op. This works perfectly if the relocations point to a space near the executable. But this, however, does not always have to be the case, as the runtime, which is often called, can be anywhere in the memory. To help with this problem, we discovered a way how to make sure as many relocations as possible will be optimized. It works by scanning the Linux memory mappings for free space near the VM runtime and requesting this specific address from the mmap system call. This way, the code is JITted into a place we choose. In our testing, the relative addressing became possible for 82% of relocations, and the performance of using relative addressing versus absolute addressing improved by 9% across the board. It is important to note here that this could also be more difficult to port to other platforms, as they might not allow access to this sort of information, but this works on Linux. To conclude our efforts, we built a functional prototype able to compile any R function into native code. It took around 1,000 lines of code, changes in the GNU R virtual machine, which are almost exclusively just exposing symbols that should usually be hidden, to be able to use them for our JIT. The bytecode implementation took around 2,500 lines, being ported from the GNU R, and finally, the copy and patch engine itself is built around 1,200 of C lines. The compiler is implemented as an R package, but at the moment requires the use of modified GNU R environment, as we've discussed with the exposed symbols. If GNU R decides to build an interface that compiles, this could hopefully change in the future, but it's not at the moment. The prototype we made at the moment also supports only the x86 64 Linux architecture. So to move on to evaluation, we evaluated based on 3 points: the performance of the code, the compilation size, and the compilation speed. And we evaluate this on 57 benchmarks in 4 suites. So first, the Me suite, which is a micro-benchmarking suite made of pathological cases of things that are usually slow in R. Then the RV-Fast suite made by Stefan Marr, who tests algorithmic benchmarks. The Shootout suite, also testing the algorithmic kind of programs, and RealThing, which are the real-world R packages. And we tested using this configuration. So to see the performance graph, so the geomean speedup compared to GNU R is 1.26. And while this number is mostly driven by the micro benchmarks, as we've seen below, the real packages also show significant improvement of 1.23 times the performance of GNU R. It is important to know here that this performance benefit does not come just due to the use of copy and patch, but could be due to many differences how the stencils are extracted and compiled. So to move on to compilation size, we see that the stencils range from 6 bytes to almost 3 kilobytes. And the instructions in R are actually quite large, which compared to, for example, the CPython implementation could be a problem because it also results in quite big programs. And on average, each instruction has around 30 holes to patch. And to move on to compilation speed, we actually achieve 980 instructions per millisecond, which results to around 0.2 milliseconds per program on average. With such a speed, this allows for almost free recompilation and can therefore be used, for example, for feedback recording. To show something about the related work, as I've already discussed for the CPython, so this is different from our implementation in a way that the CPython compiles traces instead of functions, and they can directly reuse the instructions from their implementation. There was no need to extract it like we did, because the implementation in CPython can be used standalone as shown, and it supports all platforms and but the speed up that it achieves is just the same as it was before of 1.0. The reason for this is that the bytecode interpreter in CPython is already very optimal, and many optimizations before the JIT are before the JIT is even invoked, are already performed, which is not the case for R, which didn't receive as much love for the contributions. So in conclusion, we have successfully implemented the copy and patch for R, achieving the speed up of 1.26 compared to GNU R, and very fast compile times of just 0.2 milliseconds on average. As future work, we plan to integrate it as baseline JIT in a project focusing on creating new compiler infrastructure for R. Thank you.
Interesting. Okay, we have loads of time for questions. If anyone has a question, come up to the mic.
Is this on? Can you hear me? Is this on? Okay. Hello, Jeffrey Young from Epic Games.
Hey.
You report an average speed up of 1.26 times.
Yes.
But I'm curious to know what the median speed up is, or
Oh,
confidence bounds on that.
Oh, this
or
is the geomean speed up that you see here. So,
Okay.
like these are all the benchmarks that we had. So
I see.
Yeah.
Yeah, and then can you go back to the dot plot?
To what? Sorry.
The scatter plot.
Oh, yeah. This is for the
yes.
compilation size.
I would be interested to see what just the baseline RJIT is doing, just like the not your work, but I would like a comparison here with your work versus what was standard.
I see.
Yeah.
Well, here on the scatter plot we see the compilation size, which is, but like for here we are comparing to the GNU R actually.
Yeah, I would like to see the compilation size difference. Like I guess you said it's 6 bytes to 3 kilobytes, but I guess I'm just curious.
The bottom line is the number of bytecode, and the R doesn't have a JIT.
Yeah, the R doesn't have a JIT besides the bytecode compiler.
I misunderstood.
This is really a horrible blow up of size.
Yes, because it's
1,000 bytecodes, you get 500 KB.
right. Yes, it's very fast. Okay, thank you.
So my question is, I'm wondering if you handle the polymorphic dispatch over type situation. So like my understanding of you from your talk is that you profile types by like self-modifying the bytecode, right? And for example, in the for loop case, I mean the example, there's like for int or something like that. And I wonder if you handle cases where you have seen two types in the same instruction, or do you just support like single type and then go back to dynamic dispatch if you see multiple types in the same place?
So we create all the stencils that are for all the types. So there are like 10 types,
right.
So we create 10 stencils, and there's always just one type in use during the for loop.
Sure.
So if it changes, the start for also like emits different stencil, like each time that the for loop starts. Is that what you are asking?
I'm not like specifically concerned about for loop. Like I'm wondering, like, is there a case where a single code site needs to support multiple types, like needs to have like support multiple dispatch targets from, for example, like are there method calls that need to handle different receiver types, or is it not a thing in R at all?
This is not the problem here. What I've shown that so these instructions always just use one type. When there are instructions that actually have to specialize multiple types, the dynamic dispatch is still kept in the instructions, because we cannot do anything about it for some instructions. But for those that we can, we did.
Right. So like you said, that will be going back to the dynamic dispatch instruction for supporting like the types you don't know of, or like, yeah, just so like my question was more like, if you self-modify the bytecode to provide things, and if you, for example, the stencil have like a single type, specialized for a single type, then when there are cases, the single instruction needs to support a particular set of types, then you might, it's kind of harder with this approach to sort of specifically support for these set of types compared to like just doing the dynamic dispatch and then support everything. So like, is it the case, or like just not relevant to your like our language, I guess?
In there can always be just one. There's
Okay.
not, yeah.
All right.
Okay.
Thank you.
Yeah. In the
Yeah,
case of the
sure,
for
sure,
loop
sure.
and the LD cons
So
that we've
like,
shown, it could be just one.
You're saying the for loop situation applies to everything else as well, like?
No, it's like the for loop and the LD cons that we've shown have always have just one, but the others sometimes they can have a lot of the types that they support, and we still need to include this. Like the dynamic dispatch is still in the instructions just for the for loop that we've shown.
Right. So not for the sorry then. So what would you do for other instructions that are not like for loop then?
Yeah, well, I guess we have to keep it in the stencil, the dynamic dispatch, because like if we cannot tell during the compilation which type will be there on the stack, we also cannot do anything about it.
Okay. All right. Thank you.
Thank you for the great talk. If I understand you correctly, when you are creating those stencils, you are putting the machine instructions directly, and you're not optimizing the final stencil, right?
Yes.
Did you explore applying like optimization, like instead of emitting instructions directly, translating to C and then running it for optimizations to see if there's a better speed up?
I'm sorry, how?
Like by leveraging something like GCC, then you can maybe get better machine instructions, right?
Yeah. So you mean like emitting all of the code in C and then compiling it together
Yes,
to
exactly.
executable? We have actually tried that.
And what were the results?
It was around the same actually. The
Interesting.
performance was around the same.
Okay, thank you very much.
Yeah. Thank you. Okay.
Well, so you had the problem where you want to make sure you could fit within the range of a 32-bit
Yes.
jump, and the solution was to be careful about the memory placement where you were putting your code. But what I didn't understand was what was your previous, because if your solution is we allocate memory in a special place such that we know we can stay within 4 gigabytes essentially, what were you doing previously that meant you could not be sure of that? Right? Were you just using malloc or something that could place it anywhere in the address space? Or
So if we cannot reach the instruction from where the code is jitted, we use the global offset table that we put very near the jitted code, so that it can reach this relatively, and then there it contains the.
But my question was, how did you end up in a situation where, because to me 4 gigabytes is quite a long way, right? So
Yeah.
how did you end up in a position where you could have things be spread about the address
Oh, I
space?
see. So like due to how the ASLR works in like the operating system, like it spreads the dynamic libraries across the memory. So it happens very often. Like for example, during the development, we noticed that the math library was being loaded somewhere else from the error runtime completely, and this forced us to do
So
this.
I think what I'd missed was that these are not just jumps from one piece of JIT code to another. These could be jumps to external library routines. Okay.
Yes.
So in that case, you still do have to worry about far jumps sometimes, but you sort of avoid them in the common
Yes.
case. Yeah. Cool. Got it. Thank you very much.
Thank you.
Do we have any final questions? We're still a little bit ahead of schedule, but we can also just move along to the next talk. If we don't, okay, let's thank Mate again. That's great.
Okay, thank you.
We seem to have a 5-minute gap deliberately programmed into the schedule here. Is that intentional? That's quite interesting. We could actually take a 5-minute break if that's, I don't know. So we should break for 5. Yeah, I'm up for that. Okay, let's take a 5-minute break and then. Yeah. Okay, we are back. We've had our 5-minute break, and it's time for our next talk, which is going to be from Koichi Sasada, talking about Astro, an AST-based reusable optimization framework. Go ahead. Thank you.
Okay, thank you. So hi everyone. So I'm talking about this talk. I'm from Stuart from Japan, and I'm one of the Ruby committer, the author of the current virtual machine. So I use the Ruby language to explain this presentation, but this presentation is not related to the Ruby language. So, and if you want, so this slide and my paper is published on this URL. Anyway, so today I want to introduce so today's question is how to make a interpreter very in easy way. So our solution is partial evaluation with very easy method. So we outsource any native code compilation to the C compiler, and we invented how to make a partial evaluator only with very straightforward, not complicated transformation. And another idea is naming the AST node with the Merkle tree to reuse the compiled code across the different processes. So let's introduce my motivation of this research. So of course, so maybe everyone understands this presentation. So this page. So if we have a program, so we translate to the AST after syntax tree, and so the most easy way to learn this program is tree walking interpreter that was used in Ruby 1.8 maybe 20 years ago. And after that, so of course it is slow, easy to develop, but it is too slow. So most of program language, we invented the virtual machine here. And after that, the virtual machine is also slow, so we make the native code translation by the LT or just-in-time compilation. That was introduced from the Ruby 3.1. So it is a very commodity strategy to make an interpreter faster interpreter, but it is too complicated to make this pipeline. For example, if we want to introduce a new syntax to the language, so we need to change the bytecode interpreter, and we change the native code compiler for. So it is too complicated, and especially I don't like to write assembler program anymore. So the question is how to make a interpreter, fast interpreter. So thank you for yesterday's Professor Masahara's keynote. So partial evaluation is introduced. So the partial evaluation, with the partial evaluation, we only need to write the behavior of the AST interpreter, AST traversal interpreter here, and the partial evaluator specialize the AST interpreter with the given AST and make a optimized node. So the important example is the TOEF and GRAL framework. So TOEF GRAL framework provides partial evaluator for the Java program. So any target language, and the user only need to write a Java interpreter for this language. And the TOEF framework specialize this AST to the native to the intermediate representation, and GRAL compiler compared to the native code. So highly optimized native code. That's great. So we only need to write the behavior of the each node execution. But so it's solve the my question. So the language, to make a language, so we only need to write the behavior of the interpreter, so each node, but we need to use the Turk or a similar framework. So it is so huge infrastructure, and it is difficult to modify. It's difficult to use for me, especially so at least for me. So the next question is, can we make a lightweight partial evaluation framework? So for example, if we want to support the RISC-V assembler, RISC-V machine for the GRAL compiler, we need to spend many engineering effort to modify the GRAL compiler. So we need to get the way to generate a highly optimized code and widely available, so everyone can use, and they're easy to use. So the answer is, of course, the C compiler. So C compiler, of course, so in this room, I believe you can use the C compiler or C language. So it is very easy to use. Maybe, I'm not sure. But so our tool, Astro, generates a specialized C code. And we can get a highly optimized code. So our tool, AstroGen, written in under 500 lines of Ruby code, generates an interpreter with the specializer, the partial evaluator for the given AST. So we invented two ideas. So repeating that, so we invented our partial evaluator generate only specialized dispatchers, the tiny C snippets, and we can make a specialized C code for the given AST. And the code compiled for such a specialized C code, we can reuse it using the marker hash for each AST. So after the compiling, so we can use this compiled optimized code within another processes, interpreter processes, and so on. So this is a total workflow of the Astro. So we need to we only need to write a node definition. So which nodes are there, and what's the execution behavior for this node, each node. And our tool, AstroGen, generate many C source code, includes the definition of each node, the evaluator of each node, and the dispatcher for the evaluator function, and hash function, allocator function, specialized function for many utility functions. So of course, we need to write a parser for the language. I believe, so I understand that the many compiler classes in university, so it's spent many times in parser, so I believe that people can write a parser. And so, of course, we need to write a parser and make a AST for Astro. And after that, the Astro generated interpreter can run the baseline as a baseline interpreter. So baseline interpreter can run the target program P, but it is slow because it is only a tree-walking interpreter. But this baseline interpreter has a specializer for the AST, and it can generate a specialized C code. And specialized C code, so we can make the piece of the compiled optimized native code. And if we load this compiled code at the runtime, so it can be just-in-time compiler. And if we contain the compiled code with interpreter, it can be a simple compiler for the program P or a specialized interpreter for program P. So let's try to explain the Astro framework with very small language. So we have three nodes, so num, add, and mul. So in the node def, so there is a three. We need to start with node def. So it is a signature of the start of the definition, and the node num is the name of the node, and so it seems a parameter, but it's declared that this number node has n field. So number node has the actual node the number information, and this explains the behavior of this node. So node num only returns the field number, and the node add receives a child node, LV and RV, and evaluates them, and adding the evaluated results. So I think there is no question about that. So it is very easy to write. So Astrogen generates the nodes, the header, so you don't need to write a header, so struct declaration anymore. So Astrogen generates it automatically, and each node has a set of functions like dispatchers, specializers, and hash function, something else, and each node has the name of the dispatcher. So you don't need to write this kind of boring definition of the structures. And after that, Astrogen generates the evaluator as a tree walking interpreter. So for our framework, we split the evaluation function to the dispatcher and evaluator. So evaluator, so eval, this one, receives the context, so that's language specific, and the node itself, and the extracted field, and the body of the behavior. So it means that so it's only copy the behavior, so there is no difficulties. And the dispatcher is a key idea for that. And this dispatcher calls this evaluation function with the extracted field. So in this case, dispatch node num extracts the number from the field, the node itself, and pass the node number, and run this code. So of course, this is very simple C code. So the C compiler can inline dispatch node num with eval node num. After so this is a internal node case, and it has only a bit trick. So not only copy the not only list the parameters of the node def, then it also adds the dispatch function for the child node. So all of nodes has a dispatch function, so we can get a dispatch function for this one, and so to invoke the dispatch node add function, then pass the child node with the function pointer to the dispatch function for the child node. So this function is passed, and the eval arg simply calls the corresponding dispatch function for LV. So in this case, so eval arg LV means calling this pointer with the context. So it's only small changes, and I think there is no difficulty too. So just now we have a tree walking interpreter, and we can get a dispatch function for the root function. So we only need to run the eval macro using the root node dispatcher, and can run the tree walking interpreter. So it is only a tree walking interpreter. So it's still slow interpreter. So we need to introduce the partial evaluation. But before explaining about the partial evaluation, so I want to introduce another concept, another idea. So marker hash. So marker hash is known as a tree hash algorithm for the tree structures. So for example, Git repository using the marker hash to maintain the Git repository. So in this case, so we can calculate the node hash value from the leaf node num 2, and this one 2, and so this node the hash value of HMAL can be calculated with each child node, and the same algorithm we can get all of the node hash value of the nodes. So the partial evaluation. So let's try to introduce how to make a partial evaluator for this on the Astro framework. So we don't manipulate any method definition body, but only make a specialized dispatcher for each node. For example, if we want to specialize the node num, then we generate the dispatch function with the actual constant 2. So in this case, so the general one, it reads the number from the node, but we already know that the node number, the actual number is 2, so we can simply pass the number 2 to the eval function. So after that, we can get the dispatch function for the node num 2 and node num 3 for each dispatch functions. So we can pass the node specialized function for this one and this one, and for this actual AST subtree. So repeating this algorithm, we can get the all of specialized dispatcher. And thank you for the C compiler. So if we pass the concrete program pointer, then the C compiler can inlining all of the tree, and then this code, so specialized dispatcher, only become returning the 7. So these 3 instruction for the Intel architecture. So this is what our specializer does, and we can get the compiled code for the AST, and we can get name for that. So okay. So with this idea, so we can make an interpreter for the simple optimization as a super instruction or super nodes, or compile program specific specializer interpreter, and the profile guided compiler, or just-in-time compiler. And the compiled code can be contained in a process, or we can put these compiled code outside of the interpreter, and the interpreter processes can share the compiled code. So we make a preliminary evaluation. So we make a very, very small subset of the Ruby, so named NaRuby, not a Ruby, and without the object-oriented, so many rich functionality from Ruby. and it has 21 types and 300 node depth definition. So, and we have so to evaluate the dynamic language. So the function calling is lazy binding, and we introduce a call cache, and the call to node assumes that the cache node can be a bigger ST. So it's I introduced this idea to evaluate the profile guided compilation. So we evaluate on some setting with the corresponding C code with some C optimization flags, and also our compiled code can run on the disk file because we have a disk file C compiler. So checking the results, the interpreter. So compare with the tree walking interpreter, of course it is very fast, and the C compiler optimize the empty loops. So with the null operation, and the call operation can be optimized with the program guided one with the node call 2. So we have many discussion, but there is no time. So please see our paper. So we have many open questions and some limitation for this approach, and we have many related works. Okay, so conclusion. So we introduced the Astro framework for the lightweight partial evaluator, and making so we can evaluate a preliminary evaluation with Narubi, and it demonstrates that the GCC, so corresponding GCC OZL approaching to this C compiler's C language's performance. Okay, so that's all. Thank you.
Okay, we have a couple of minutes for questions. If anyone has a question, would like to go up to the mic.
Thanks. Okay, thanks for your talk. So as you could know, so Truffle is now focusing on bytecode interpreters. So I'm curious about this approach is applied to bytecode interpreter generation. So how do you think about it?
Yeah, so because so the reason why we concentrate to the ST, because it is easy to inlining the functions. So if we get ST with caller and query, so we can natively connect to the caller subtree, so we can get a bigger ST without complicated things. So this is why we choose ST for optimization. But of course, so we can calculate the hash value for the bytecode. So similar idea we can use, I think.
Okay, thanks so much.
Hi, thank you for the great presentation. Someone from NYU. I had a question about your assumption that most languages provide an AST, because as far as I know, Lua does not have a AST definition, does not have an external facing AST definition. I think Ruby also did not have like a unified parser until very recently. So is it true in practice that many of these interpreted languages come with an AST, or could it be the could it be the case that languages actually kind of have converged on bytecode as some sort of unified interface for other interpreter implementations?
Yeah, I think it is an interesting idea, but I'm not sure we have an impact for other languages. So I'm happy to get AST representation for each language, and I want to try Astro framework for any other languages, but I'm not sure the people what the other language authors think about that.
Thank you.
Okay, great. I think we're about on time now. Sorry? Oh, go for it. Please, please, go ahead.
Hi, sorry, I've left the mixing desk for 2 seconds. Thank you for a really interesting presentation. I'm Finn from the University of British Columbia. I'm curious what your thoughts are on memory management. I know for simplicity you skipped it in your evaluation, but given your dependence on C, which has no really helping for this, how would you add such a feature?
Right, great question. So I need to put the memory management on the open question. So for example, so using Java, so we don't need to have we don't care about the memory management because Java has a garbage collection. But I'm not sure the Java or other managed language, managed language can make a good performance. But so because we use for the performance reason, so we use garbage collection. We use a C language to make this framework. But for example, so if the answer is I'm not sure we can use the garbage collection managed language to use this one for the performance. But so for example, C-Ruby, so we are making a C-Ruby interpreter and written in C language, and we make our own garbage collector. So we can, I think that we can make our own garbage collection for that. But it's maybe it is a separate topic for the Astro.
Thank you.
Great. Let's thank Koichi for a great talk. I think that we're out of time now, so we're going to move on to the next one. But thank you very much. This was great.
Thank you.
Okay, so our final speaker this session is Humphrey Birchall from the University of Kent, talking about how to make programs slow down reliable. Take it away, Humphrey.
Thank you. Yes, and also I mentioned I did this work with Stefan as well. So why would you actually want to make a program run slower? Well, there are actually a variety of use cases. Profiler accuracy. When you actually want to evaluate the accuracy of a profiler, you might want to use such processes as causality analysis or profiler divining, which is an approach that we've proposed in a UPSLA paper, which I recommend you come to my talk on Saturday, and I'll explain more about how that actually works. Exposing race conditions, it's terribly useful if you can make certain sections of a program run slower than normal, and this can help actually expose situations where a race condition could occur. Implementations such as chess or waffle actually use some form of deliberate slowdown to actually create race conditions or see them. And finally, virtual speed up. This is a implementation. This is a proposed technique implemented as COS. What they do is deliberately make sections of the program run slower, and then this actually lets them see optimization opportunities from the sped up code, which is just the code that isn't slowed down. And they would definitely are after a reliable and accurate slowdown. So the goal of the paper and this talk is actually we're going to evaluate x86 instructions and see how good they are for being used as actual deliberate slowdown. The requirements we have for each instruction is how accurate are they? If we want to make the program or a basic block run 100% slower, can they actually get to that level of slowness, and how reliable are they of being that slow? Side effect free, you don't want to add instructions and then you've changed the performance behavior of the program. You don't want it to now run differently. Particularly for stuff like COS or profilers, if you're trying to check how reliable the slowdown is, you don't want one method to now be the entire execution when it's slowed down, but not when there is no slowdown. And distributed slowdown. You don't want to achieve slowdown by actually just making one single block consume the entire slowdown execution. You actually want to try and distribute it and make all areas of the program run slow, but at the same level. We're going to achieve slowdown at the basic block level. Basic blocks are just general ways to organize machine code. They have one entry point and one exit, so there will only be one jump. Why it's useful to use these for slowdown is once you've actually added slowdown into a block, if that block is executed, the slowdown is guaranteed to be executed. So it's a good area to target slowdown. We're also working very, very late into the compiler, almost the last optimization phase. So we're working nearly on the final emitted machine code, which means we're avoiding interfering with compiler decisions such as inlining or dead code elimination. So we inserting shouldn't have an effect on decisions and therefore change the program behavior. To actually determine how much slowdown to add, we're using hardware counter feedback. We used vtune, and we added slowdown into a block and looked at a vtune report and see how much increased amount of time did we add to that block. And then we just iteratively added slowdown until we could get as close as possible to a target slowdown. Our setup, we're working with Java and the Graal compiler specifically. We're making use of compilation replay, which is where you do an execution and it logs how it did the compiler, what compiler decisions it made. You can then refeed those decisions, and then the compiler will try its best to try and repeat a similar execution. This should hopefully remove a lot of noise and non-determinism we would see in our results. And we're using the RWFastJet benchmark suite. Specifically, we're actually only using one deterministic benchmark. We're using the Towers of Hanoi benchmark. We only did one benchmark because the setup time and that iterative approach of adding slowdown is extremely time consuming. So we thought only one was appropriate. The actual proposed x86 instructions we looked at were NOP has 0 side effects, and it's pretty much purpose-built for such things as delaying or padding. MOV is probably one of the most used instructions in x86. It's very fast, it's very highly optimized, and if you use it in the sequence of moving from one register to the same register, so for example a MOV racks, you don't actually change the value inside the racks register, but the CPU has to waste some time actually dealing with that. Push and pop, after the sequence nothing has actually changed, so this is a more heavier slowdown sequence that you could use, and we want to see that maybe a large amount of slowdown can get you to that target quicker. sfence, it's a single instruction, serializes delay, but it shouldn't actually have any effect after it's actually executed. Long push and pop, this is just a longer sequence version of a push and pop, but we actually make use of vector instructions. So this is actually to see if we kind of load some of that time to the vector unit, maybe that gives us a different level of granularity of slowdown. And pause. Specific to x86, it is a purpose-built delay. It's used to hint the CPU of spin waits, busy loops, and we thought it would be an appropriate instruction to test for this use case. The research questions we had in the paper was how close does each candidate get to the target speed? So we set a target speed of 100%. Could we get the program to run 100% slower? What distribution among the basic blocks? So to actually achieve that slowdown, we make each individual basic block of the program run 100% slowdown, so therefore the program should run at 100% slowdown. And we wanted to see, is that slowdown actually achieved among all blocks, or has just some blocks got very slow and that's just achieved it? Do they maintain the original performance behavior? This is to test whether or not the slowdown has side effects. What we did was we pointed a profiler at the program with no slowdown and then with slowdown, and we wanted to see has the profile changed in any degree. And finally, an extra question we tested in the paper, but we won't in this talk, is what effect does the placement of have within the blocks? If you have a basic block and you have many slowdown instructions inserted, should you place all of them at the beginning of the block, at the end of the block, or should you try and mix them in the block? They're all guaranteed to be executed, but what effect does it actually have if you distribute them amongst the block or at the start or the end? So, how much slowdown did we actually add? So for the Towers of Hanoi benchmark, there are 53 basic blocks that actually consume some amount of execution time. We set a target speed of 100%, and we required that each basic block had at least a minimum of one slowdown. Nopomov clearly have far more amount of slowdown. This sort of starts to hint to the degree of granularity we actually had with slowdown with the Nopomov. It required far more to get to that target speed, but they have a finer granularity. S-fence and pause, you can see it's nearly about one slowdown per basic block. So one was already enough to get to the slowdown or exceed that target speed. But actually, what was the program overhead? So for 100%, we saw that Nopomov get pretty close to that target overhead of 100%, 109, 106%. Push and pops around 202, and S-fence and long push fence around 400. This sort of suggests that they actually, using those types of instructions, have a minimum amount of overhead that they adding just one to a basic block already makes the block slower. So if you actually wanted to achieve a target slowdown of 100% or less, then these instructions are probably not suitable. Pause, very much far off. 11,000% overhead was added to the program by just adding one pause to each basic block. It's clearly not very suitable for any use case that we would for these benchmarks. What was the distribution? So we're plotting here the difference in overhead from the target overhead at 100%. So we're hoping to see that the majority of the runtime is somewhere around 0, which is 0 difference from 100%. Nopomov have definitely a shape that we're looking for. Most of the runtime is distributed around 0, and they've got quite a symmetrical shape, which shows that that we had a few blocks that were slightly underslowed, but we also then had some blocks that were slightly overslowed, so it started to balance out. Push and pop, you can start to see that it's getting that there's many blocks, and therefore the runtime is starting to get overslowed, and that's shifting to the right. More clearly with S-fence, it's just lots of the blocks are getting overslowed, and pause caused so much slowdown that it's just over the bracket and over 500% difference. Do they maintain the original program behavior? So we pointed a sampling-based profile at async specifically at the program before slowdown and after slowdown, and we looked at the percentage of runtime each method had. So even though the program is running 100% slower, you would still expect each method to be the same percentage of runtime. So therefore, the methods we would expect to be on the x equals y line. Nopomov, the percentage of runtime has stayed very similar with the program being slowed down, so you've got some confidence that there's very little side effects there. Push and pop, you can start to see that there's definitely change in the program behavior, similar with S-fence, and long push and pop has definitely completely changed. Interestingly, pause has not changed to such a degree, even though it had such a massive overhead. One likely explanation for that is because those pause operations are so heavy in terms of cycle cost, you've now just biased it to activation count of the blocks, and that has just led to a profile that is slightly similar to what it's before. But there's still definitely a difference and a change in the program behavior, so it's not very suitable for it anyway. And a use case. We actually have used this to implement profiler accuracy evaluation. For our paper that we're giving to Uppsala and my talk on Saturday, please come. We've made vector.hasSum actually run slower. We've added 5 seconds of additional runtime onto vector.hasSum, and then we're testing with 4 profilers, have they actually detected this change? Async, and the red dotted line is what we predict the change to be. Async and JFR, Java Flight Recorder, have actually detected this change in runtime, but JProfile has not detected any change in vector.hasSum, even though it's running 5 seconds slower. And YourKit has not also detected a change in that, and maybe actually is slightly decreased the amount of runtime. So this has actually allowed us to evaluate these profilers and their level of accuracy, with async and JFR for this one experiment having good accuracy, but JProfile and YourKit not so. To conclude, we found that NOP and MOV were the best instructions in terms of accuracy and side effect free and maintaining the original program behavior. Not shown here, but in the paper, we actually found that mixing the slowdown amongst the basic blocks was the best approach compared to putting them all at the start and all at the end. And this actual approach has enabled us to implement a viable approach to evaluating profile accuracy. Thank you. That is the end.
Thank you, Humphrey. Okay, questions, please head to the mic.
Hi, thanks for the talk, a very interesting premise. This is Manas Thakur from IIT Bombay. The question I have is, have you implemented it, you implemented it in Graal, but is there a way the programmer or the developer could specify an interface through which they can, where do they want a slowdown in the program, for example? Or do you plan to work on it, if not?
If I understand your question right, if you're asking about generalization, it's not specific to Graal, but we did it in Graal.
Yeah, but let us say as a programmer, I now want to specify what parts of my program do I want to be slowed down using the NOP or move instructions.
Yeah. Could you actually build an interface to actually allow you to do that?
That's the question.
Yes. It's going to be very difficult. So we did it at a basic block level, which meant we didn't actually have to care how this actually returns to source. And it's very difficult to then map that back. So yes, you could do it. You're going to have to solve the problem of knowing which bits of the original source code then actually turn into basic blocks. And basic blocks may contain multiple methods due to inlining. So you have to decide at what point. So yes, it is possible. That is the difficulty, and that's why we chose to do it right at the end when it's just basic blocks.
Okay, thanks.
Hi, thanks for the great presentation. I'm curious how sensitive this is to variation within x86. So I imagine you were testing it on a specific CPU, but obviously there's oftentimes quite drastic architectural changes between CPU generations or even, I guess, between manufacturers. How sensitive is your testing to such variation?
So we did test this only on one x86 CPU. I would imagine if you move to a different architecture or different CPU alone, you would have to redo that calibration again. It does just use hardware counters, so it should be transferable. But yeah, I would expect it won't. You can't just transfer that out of the box to a different CPU. You'd have to do it all again. You have to retune, redefine.
I see. Thank you.
Thanks for the talk. So a single basic block doesn't necessarily take a consistent amount of time to run because of things like cache misses and things like that. Did you consider how you would deal with that at all?
So that's why we used the hardware counter feedback. So we originally did build some system where we had a static guess. We knew the cycles and we had a guess at how much to add, but that just doesn't work at all. So we had to use the hardware counters to actually incorporate that pipelining and out of order execution so the value adjusts.
Did you consider how you might deal with something where like a specific basic block takes a different amount of time depending on like whether how it...
We didn't really encounter too many of those. There are in the other work, there are cases where you get a basic block which is just a test and a jump, and they do just completely change from costing a few seconds, a few milliseconds to a few seconds. Those ones you have to bite the bullet. You have to just accept that it's not going to work. And then that's where you get the variancy. It's if there was a case where that was a majority of the runtime, I think there would be a problem. But we didn't encounter that. It was only a tiny amount of the runtime accounted for those really wobbly basic blocks.
Okay, thanks.
Hey, thank you for the great talk. I mean, if you read the Intel if you read the Intel manuals, I guess they have some explanation on the number of cycles and about the performance of each instruction. So, how much were you surprised by the results if you read the Intel manuals compared to what you got?
I was surprised how stable the blocks are. Very related to the previous question, there is majority of the time the blocks do stay actually a very similar execution amount of time. Interestingly enough, single byte NOPs got completely eliminated immediately, whereas 2-byte ones got saved. But I think that was very specific to our version of it.
And for instance, for the pause instruction, did you expect it to be like that?
For the what instruction, sorry?
For the pause instruction.
For the pause
After
instruction.
reading the manuals, did you expect it to be like that? Or?
No. There's nothing in the manual that hints to that should happen. I remember the Anger Fog data says that it doesn't take. It's like 20 cycles or something. It's nothing huge, but clearly it's just not usable at all. Okay. So yeah, that one definitely surprised me a lot.
Okay, thanks.
Thanks for the talk. I'm wondering if you've generalized this to programs that will run on multiple cores, and whether that would change the instructions you use for slowdown, because SFence obviously would change the ordering sort of thing, but have you generalized this to other sorts of programs?
So no, we haven't done that yet. I would be really interested to see what effect that actually would have specifically with SFence, but luckily, well, we found NOP and MOV were really the only viable implementations, and for the other work we actually used the MOV with a similar register.
Yeah, I wonder if there's a specific angle for this where you would like to sort of focus on the synchronization instructions and make those specifically slower when doing sort of multi-core sort of programming.
Yeah. Obviously we haven't done it, but I would be really interested to see if that is a viable thing to do. Yeah.
Thank you.
Okay, I think that's the end of the session. So let's thank Humphrey and all.
Yeah, so you are going to have a till?
Yes, that's right.
Okay, so we have 2 minutes, so you can. Okay. Have you tested your laptop?
Sorry?
Have you tested your laptop for?
Not really. No.
Oh, so can you connect it? Yeah, so we have 1 minute. So okay. Yeah.
Work.
Sure. Do you have a HDMI?
I do. Is that HDMI?
Seems not.
It's not. Okay. Oh, there we go. That's slide.
Sure. Just a moment. So, what's going on?
I can see the desktop.
Yeah.
Okay.
So yeah.
Okay.
Yeah.
Yep. So I think it'll work.
It works. Yeah. So he will switch this screen to your
Okay.
monitor.
No problem.
Yeah.
All switching is manual, so if you don't
Yeah.
see it, it doesn't mean it's broken. Okay. Cheers.
Cool. Okay. Hi. Good afternoon, everyone, and welcome to the keynote and language semantics and type system session in VMIL. I'm Yusuke, and I'll be chairing this session. We have 3 exciting talks today in this session. Yeah. Okay. So first, I'm going to introduce Anil. It's my great pleasure to introduce our keynote speaker, Professor Anil Madhavpeddi from the University of Cambridge. He's a computer scientist whose work beautifully connects systems, programming languages, and sustainability. Anil is well known for his contributions to OCaml, Mirage OS, and the Zen project. More recently, his work has focused on planetary computing. Okay, please welcome Professor Anil Madhavpeddi. Yeah.
Oh, I'm glad to be here. I'm not glad to be here.
Sure.
So that's what's there.
Oh, I see.
Okay.
Oh, let me just sort this out.
Sure.
Never upgrade macOS before a conference is my lesson in life to everyone.
Oh, fine. Yeah.
All right.
So can you turn off true color?
Sure.
Yellow and nothing.
Oh, yes, of course. True color. Now, where is that? Oh, true tone, that's it. Ooh, that's exciting. The only thing more complicated than I/O is screen sharing.
Yeah, that's good. Yeah, Anil, the floor is yours.
Thanks very much. All right. So I'm really glad to be here because the first question I had when thinking about what to talk about here was, are I/O libraries really an interesting research area? Because they sound pretty boring when you look at them at face value. But then when you step back and look at the evolution of these libraries over the decades, it actually gets pretty interesting because ultimately, computers aren't very much use if they don't do I/O. We do a whole bunch of computation, but if we don't shift the data to the right places, then there's not much utility in that computation. So making sure that we keep up with whatever we need to do to feed our CPUs and our GPUs with I/O is extremely important. And if you step back a little bit, I've realized that over the last kind of 30 years, I've been actually doing the same things again and again. And I thought I would highlight some of those things in order to give you some guidelines about perhaps the direction we should go in when it comes to managing our runtimes. So back in 1996, when I started using OCaml, life was pretty simple. It was single core machines, they were spinning hard drives, and Unix mattered a lot. Like the idea that we would have a single standard called POSIX remained true and important and relevant. And then this technology called Zen came on that I worked on, where we had this idea of virtualizing machines. I'll talk more about that. And then by about 2004, multi-core became a thing. SSDs and flash drives emerged. Linux and Windows started to dominate versus Solaris and a lot of the other operating systems that were around at the time. And then, a few years later, started working on a technology called Docker, which started bringing containerization to the masses and working on different and interesting ways of doing systems virtualization. And then meanwhile, of course, the world had been moving on and hardware became really diverse. So, and today, my development machine has 768 cores. It's got 4 terabytes of RAM. I work on exabytes of data for environmental science, so processing the world's satellite data in order to come up with insights to help with the world's biodiversity. And what this boils down to is that the amount of data has increased, the number of cores have increased, the heterogeneity of how we deploy our services has massively increased, including the deployment of really exciting browser-based technologies. And there's GPUs everywhere with machine learning workloads. So where we are right now is that although we're orders of magnitude bigger, the way that we have to approach how we process this data has got to change. And for our old friend POSIX, who here knows what POSIX is? You've almost all programmed in POSIX at some point, right? And I realized that POSIX was my rubric, my idol when I was doing systems programming. When I was an OpenBSD developer, I would make sure that we were POSIX compliant. And then slowly, as technologies arrived, they began to wrap POSIX, things like Zen and Docker, and progressively, there's been an extension in the way that we process our software, and now POSIX is just an illusion. It's just a memory of something that once was, and it's holding us back. And so I'm going to try to make the case here for why, when you do virtual machine design at any level, you should not think about POSIX first, and you should move forward into new APIs and treat POSIX as very much a slow compatibility layer that is not a first-class citizen here as well. Does anyone? I see a few people shaking their heads. Interesting enough, actually. So let's see if you're convinced by the end of it. So what I'm going to talk to you about over the next few minutes is that, first of all, I'll make this case for why it's really, really important that we step away from POSIX as the way that we interface with the outside world from virtual machines, mainly because of the prevalence of shared memory parallelism. And then in the second bit of the talk, I'll talk about what some of these post-POSIX interfaces are. And just to give me a sense of how much you know, how many people here have used IO-Uring or, okay, we got 1 or 2, okay, so 1 in 3. What about Grand Central Dispatch? Any iOS developers in the audience? So actually, the same people are putting your hands up. How many of you are also OS developers or, okay, we got two of the same ones. But generally speaking, most of the audience have not used these next generation technologies. And I'll explain what they are and give you a sense of how they fit into the stack. And then, back in OCaml, in my home turf, we've been having a go at just trying to build in support for this as a first-class effort, and I'll explain the work in progress that we've been doing towards that, using lots of fancy new features in the OCaml 5 tool stack, mainly effect handlers. But first, let's look at the case for a post-POSIX system. And as a runtime developer, you're always in a slightly awkward middle ground, because you're sitting between the applications and a certain kind of hardware stack, right? And it's really hard to keep everyone satisfied. You have to satisfy the application developers who won't tell you what they're doing. And then you have to satisfy the environments you run on. And so it turns out that this story is repeated all the way through the hardware stack. And when deploying applications, it's very useful to know what that stack actually is. And the first thing that happens is that we almost always have a kernel in the way. And this kernel is ever growing. So Linux has grown to over 45 million lines of code over the last 30 years or so. It began on a single floppy disk. And the reason it's so complex is that it acts as a middleware for the world's hardware and effectively the world's software as well. And it provides high-level services like storage and networking. And it has to schedule them and provide isolation. But when you look at the kernel, it really is a kernel of two halves. The bottom half of the kernel deals with the low-level things, like how do you interface with hardware? And this is the majority of the complexity in Linux, because the reason it is so dominant is that anytime there's some new hardware, the first thing that a hardware manufacturer does is to write drivers for Linux. The second thing is to document it. Maybe the 10th thing. But really, it's all about making sure that interrupt handling and memory and CPUs are dispatched correctly. And hardware has become really diverse if you think about just what's happened in the last 30 years. And there are tens of thousands of device drivers and hundreds of classes of drivers in there. But they essentially make sure that they can take something that's coming from some I/O memory and steer it towards eventually a CPU at some point. And the way that they do this is that they use ring buffers. And ring buffers are a block of memory where you've got a producer and a consumer, and one side pushes something onto the shared memory buffer, and the other side consumes it. And at the lowest level, this happens in hardware usually. So a network card, for example, it ultimately boils down to some shared memory somewhere and something keeping track and synchronizing of the shared memory buffer. You might have one queue in the NIC that is pushing packets that are received, and then we're reading them off, and then it goes through a long bit of the kernel, and then vice versa, when I'm writing, I write to some hardware buffer. Maybe I have a bunch of copies, maybe it's zero copy, but fundamentally, this is the synchronization mechanism that we have with the hardware as well, and then a bunch of configuration as well. So shared memory buffers are what we have at the lowest level of our computers usually. Then, the second bit of the kernel is isolation. It's trying to figure out, how do I take this low-level stuff and then have a bunch of hostile processes that are multi-tenant and try to make sure that we can make these things compatible and work together. And so the kernel's job is to deprivilege something called user space, and then to provide an interface and an API towards all of these tens of thousands of device drivers. And it does this, this privilege context switch through a system call interface. And the system call interface is pretty monolithic. It is simultaneously saying, give me a privilege switch so that you no longer trust me, and you can look at my data, and then you can access the privileged hardware. And also, it's an instruction to do something as well. And it's a fairly synchronous process. So the system call interface is quite a request response with synchrony built in, and it's the primary API that POSIX specifies in order to do things with your computer. So any process will always have a syscall interface as the only way to do side effects. So without that, you've got a process that is effectively functionally pure because it's got no way of having the results materialize elsewhere on real hardware. And then we finally get to the runtime, the bit at the bottom of the stack that has to go through all these layers. And this layer is usually uses something called libc, which is a C-based compatibility layer over syscalls. So this is the quote-unquote portability layer. And this abstracts the very low-level part of the syscalls into a C-based API. So one that is not assembly-based, one that is more or less architecture independent and can make these calls. And this is where standards like POSIX have historically specified what you should do when it comes to making function calls. So this standard works across kernels, and it works across architectures. And this is then what our runtimes usually link against in order to talk to the world. But you can see here that the stack is pretty big, right? When you're looking at this already. And we're only about 2004 here. And the problem here is that as our machines get more and more multi-core, we have to, in our runtimes, figure out how to use all these resources, even though they're multi-core and NVMe and flash and so on. And it's really difficult to do this without some cooperation. And the problem is all these layers tend to fight each other at a scheduling level. So multiplex scheduling is when you have two schedulers trying to schedule the same resources, and then they inevitably fight, and they're just not as effective as having one scheduler. And so it's quite hard to use all of this. And so obviously the answer is to add another level of abstraction. So because it's so hard, we thought, let's just carve up the machine into smaller pieces, and then now we can schedule these smaller pieces, and we don't have to schedule across those, and that's what hypervisors are. And so that's what we use in the cloud. But effectively, we've now got yet another layer between us and the thing that's actually doing the work, the hardware. And there's tens of billions of virtual machines in the cloud with this. But the way that the hypervisors work is very relevant to this argument, because what a hypervisor does is that it tries to give you safe isolation to real hardware without having a performance impact. And the way it does this is by patching the kernel to fool it into thinking it's running into real hardware, or using some hardware instructions, a combination of both. And then it has a mechanism by which it can give you the virtual device drivers to the kernel, which are then used for everything downstream. So you don't have to make any changes to your runtimes or your applications. And how do these things work? Well, they essentially work through a sequence of rings, and these rings are mapped either to the real hardware, so known as a backend driver, or into the front end, which is the kernel that has been virtualized. And then ultimately, we've got something where requests are pushed in into a front-end driver, and then the hypervisor then looks at the requests. It just gives them a quick once-over to make sure they're in the right region. And then it sends it to the real hardware, which itself has rings, and so it can be quite efficient. And a well-designed hypervisor, like Zen, can make sure that it uses hardware support for this checking to be really fast. So usually using page tables or other mechanisms. And what this boils down to is that these rings are actually quite well aligned because they're both mapping onto the same underlying kind of constructs. And once you set up the channel, your data path is very, very quick. You're just flipping memory around, and it's like you've set up a highway for these things to go down. So it works okay. And then they're still fighting each other, and so you have to be a little bit careful about how you make these things kind of work together. But then, unfortunately, because of that fighting, virtualization was quite heavyweight by about 2014. And so even though we had a few billion virtual machines, there was no real genuine sharing going on. And so Docker came along and containerization. Docker kind of glued together a lot of pieces in the technologies that made containerization, but it's essentially another layer of virtualization, but at the namespace level. So when you try to open a resource, instead of having a full virtual machine and kernel, in things like Docker, you can share the kernel, and then the names of the resources you try to access are shimmed. So if I try to access, for example, /root/Alice in this case, then it will actually, inside a namespace, I can just make /Alice my root, and I'll never be able to escape. But once you open that resource, it's just like a normal kernel resource. And again, it goes through a bit of a fast path of POSIX and so on. So containerization was a useful way to provide lightweight name-based multiplexing while sharing the kernel. And it also then uses shared memory in order to make various transitions as it goes through its data path. So if you're a runtime developer, you're designing a new virtual machine or an existing one, there's quite a tower of cards here. It's kind of a miracle sometimes that computers work. But all of these things are where you have to go through in order to just send a packet or read a block from disk. It's just most of the time it's hidden away. Now, we have a bunch of shared memory rings here. And this is how computers stay reasonably fast and how we can partition up resources. Until POSIX, where you've got a bunch of syscalls, and it's like you're driving along at 150 hours on a motorbike on a very safe path, and suddenly you've got to make some control turns. You've got to synchronize, you've got to stop, you've got to have privilege checks, and this is fundamentally almost impossible to parallelize. And so if you are working in this stack of things and you care about performance and you care about getting the maximum bang for buck out of your very expensive kind of modern multi-core hardware, this is the bottleneck that defines all of the bottlenecks when it comes to any kind of I/O in your systems. And so it's really, really hard to kind of make that work. And reflecting this fact, there has now been a concerted move across all operating systems and browsers and everything else to basically bypass POSIX. But we haven't quite realized it yet as well. So for those who are shaking your heads, are you now reasonably convinced that POSIX is a bad thing when you see the stack? Okay, I see a couple of nods. It's surprising how much you can forget the layers of software and hardware kind of behind every simple operation that you do. But really, the rubric is that if you've got a bit of memory, then you can do very fast tricks with memory to make them go across multiple layers of abstraction without any real performance impact. There is some, but not a huge amount, and you can go at kind of near wire speed. As soon as you take page faults or any kind of other control operations, things get really slow. And so what are these post-POSIX systems that we want to think about when it comes to developing them? So let's have a look at what that is now. So we now know it's okay to just start designing things without POSIX, but let's understand what it is first. So the essence of any kind of system call in an operating system is that you first of all, you decide what operation you want to do. You pack it up into a C function call, which then becomes a bunch of arguments that it's hardware specific. It's either goes in the register for a hardware instruction, or it can be packed into various other kind of instruction formats. But the kernel then doesn't trust anything about what you've given it. If you give it some memory, then the kernel will pause the process. It'll either copy memory into its kernel space, so user space can no longer modify it sneakily through a parallel process. It then executes something, and then it returns. So for every single call that you do, there's quite a lot of work that happens. And so this is an S-trace. So this is the result of showing you what happens at a syscall level whenever, in this case, I'm just doing a simple read and write. So you can see for this process ID, the fact that we're reading some value. We've then got some threading-based synchronization, because in order to let the user space process continue, you need some way to make that synchronous thing asynchronous. So this is now blocking. You've got poll, which is a somewhat legendary instruction that almost all of you who've used POSIX have used, but has subtle variations. It's quite hard to scale. You have to pass in all the FDs statically, and then you're polling for the result. A whole bunch of thread synchronization thing happens, and then you're finally running a result. And this is for one resource. And so you can imagine that if you're doing things at scale, so a modern machine, my machine has 4 terabytes of RAM, so it can handle millions and millions of processes. This synchronicity is a bit of a death knell to doing anything performant. So what does it look like if you step away from this? If you have a fun Sunday morning where you're thinking about life, it's always worth reading the Linux kernel. Because this is what Stephen Dolan has taught me. Because it turns out that there's loads of system calls beyond POSIX where just by flicking through the manual pages and the header files, you can actually discover a whole world of new interfaces, some of which were bad ideas, but you can still learn from them. And Uring, which is the newest kind of game in town, TBD if it's a good or a bad idea, but it's definitely an idea. And what it does is that it gives you rings, just like we've seen with the Zen and the network cards. And the basic idea here is that we have 2 rings, a submission queue for requests and a completion queue. And these are just normal memory pages mapped in at a configurable size. And what happens is that applications submit a request from user space just by writing something to the shared memory ring. And you have a producer and consumer pointer that decides where you're going to write based on an index. And critically, when you write the request, your runtime can decide some arbitrary user data that we'll then come back to later on. And the set of operations you write are just C-based operations, where in this example here, there's a full link, if you look at my slides later on, which shows you the kind of operations you write. You can read and write and poll and send messages and things. It's very similar to the syscall interface, but not entirely complete. And then you submit these, and you submit a whole bunch of these things, and then the kernel goes off and does the work, and asynchronously at some future point, and out of order, writes CQEs in, which are the responses to this thing. And the way that you tie the completion queues to the submission queues is that user data, that pointer that you passed in, is maintained by the kernel and tracked, and it just gives you that back. And then it's your job to dispatch everything, read the responses from the completion queue, interpret the result, and then pass it back to your mutator as well. So the CQE here, the struct, is very simple. It's just the user data, the result, and a bunch of flags about some metadata about the request, which I'll come to later on. So the essence of this is that the amount of work that you do when you send a request from a syscall level is algorithmically better. So this is for a bunch of parallel requests, and the only thing I need to do into the kernel from a systrace perspective is call one thing called IOring enter that is a signal that there is something in the ring. Later on, if people are just pushing things to the ring, I don't even need to do this syscall, because the kernel will just note that there's unconsumed requests, and it will just continue to poll, and it will stop polling at some point, and then whenever I see that the ring is empty, I just give it a prod to wake up again, and that's it. So we've gone from this rather busy thing per process to something that's quite relaxing. You're just saying, here's a ring, I'm going to keep putting stuff on there, and I'm just going to tell you whenever you need to wake up and do something about it. And then you can, at your own time, look at the completion queue, and hopefully not too lazily, because you'll drop events if you take too long, but you can consume it at your own pace as well. So we've decoupled the synchronicity in the kernel now. And crucially, we've also decoupled the security context switches and all the other things that happen as well. That's all part of the Uring protocol. So U-Ring has a ton of features to further increase performance, and these map onto the kind of things that you have in hardware. So things like link requests, you can do multiple writes, and they act as memory barriers, so that you can stop. They can go out of order across the barriers, very similar to memory things. You can even steer requests towards particular cores, so that you can control where the memory heads to. So in a NUMA architecture, you can control your latencies as well. And a bunch of ways to make repeated operations cacheable. So fixed buffers mean that you don't have to register the same memory buffers all over again, and you can further minimize the amount of thrashing that happens. But, there's a but. In order to do this, it's extremely hard to retrofit an existing application to use as POSIX to take full advantage of this API, because it's so much richer. You've got the ability to submit batches, they're linked, you're essentially submitting a data flow graph to the kernel, and then asynchronously reading it back as well. So again, POSIX will hold us back if we do too much of that. And you also have to make sure that your buffer management is top quality. If your buffer management is a little bit fast and loose, as has been on occasion the case in my code in old school at Campbell, then things go very rapidly wrong because of the amount of concurrency here as well. So you could get away with it in POSIX sometimes, but not really here as well. You're trying to minimize copying and maximize throughput. And so the interesting thing about U-Ring is how similar it is to further downstream hardware interfaces. And the same kind of questions come up in operating systems and in runtimes and in the way that we manage U-Ring. You need to figure out how big should this ring be, what do you do when it's full, how many threads and cores do we map these rings to? These are new questions when it comes to I/O management in Linux, but they're very old questions when it comes to questions of what runtimes do and what operating systems do as well. So I'm hopeful that this part of it is something that's really quite manageable. Then there's a slight downside. Although there's similarities to the way that it works in other bits, there's one kind of slight problem, and that is it became a really good way to make money. And so whenever you've got these synchronous calls to the kernel, Linux historically is actually not synchronous internally. It's got a lot of state that means that it can block internally whenever it comes to doing things. So suddenly we've got a user space API where we can submit bazillions of asynchronous requests to Linux, but internally the kernel is now forced to do a bit of a control inversion and then store those in some kernel resources. And this is anathema to the kernel, because the kernel hates having to allocate memory. Because if it runs out of memory, the only thing it can do is to start destroying user space processes, and the killer comes along. And this usually kills the biggest allocator of memory, which is usually the runtime, right? So the big managed runtime that's trying to get a whole bunch of other work done as well. So this is a disaster if this happens. And so U-Ring has exposed a bunch of architectural deficiencies in the Linux kernel. And so there's an enormous kind of hygiene cleaning going on that might take the rest of the decade, but it's important that it happens. And so Google has actually suspended, before you all go off and find more vulnerabilities, it suspended its vulnerability notifications because there was just too much being paid out. You can see here that the IO ring was the majority of CVs in the kernel in 2023. It's still happening. More features are being added, and more things are being found. But there's an expectation that the architecture of the kernel knows what it needs to do next as well. So just bear in mind before we switch to this thing, it's not a complete panacea, but this is the direction of travel that I'm arguing for. The surprising news is that there is a kernel that is actually quite asynchronous internally and has a rather beautiful setup. And unexpectedly, it is Dave Cutler's NT kernel that is still at its heart in Windows, actually quite an amazing asynchronous I/O heart. Where Windows kind of falls over is it's kind of the opposite of Linux. The user space interfaces are appalling to use. There's just many, many variations. But the kernel is one of the most beautiful kernels I've ever worked on. And this means that finally Windows can have its shining spotlight in the sunny day, because Windows can actually have a U-Ring style API where it can handle the asynchronicity effortlessly in the kernel, and then therefore not have all of these CVs. It's got security issues for other reasons, but not for this particular I/O interface. And so Windows, although being Microsoft, they couldn't quite resist giving it loads of names. So there's a separate set of APIs for file system management called IO Ring, which has a very similar interface to IO U-Ring, and then for networks called RIO. And overall, the overall term is called overlapping I/O. The idea that you can essentially submit these requests and have it overlap for some reasonable amount of time. So this is good news, right? Because in our major operating systems, Windows and Linux, we've got very similar looking shared ring APIs. So we're good. We're good to go, right? Security, apart from security. The problem is our old friend macOS. So macOS also has wanted to expose this concurrency for a long time. Ever since the shift from PowerPC to Intel, macOS has been going more and more multi-core. And it's got a very complex mechanism of queues where the kernel and the user space can declare their concurrency requirements, and the kernel can then independently scale its kernel-side resources or its user space resources through a mechanism known as libdispatch or Grand Central Dispatch. If you've done any kind of iOS programming or macOS programming using these native APIs, you will have seen these interfaces. They permeate all the way through the stack. But the slight hitch is that they don't expose enough information. They still only expose these queuing abstractions and not the shared memory rings. So it means that there is a scheduler hidden in macOS that will be fighting with the runtime, and you can't make these harmonious as well. But we'll come back to macOS. Apple's always a little bit awkward when it comes to building these APIs, but you can, in theory, get the performance out of it as well. And then after this, we've got our friends. I've lost my keyboard entirely. Oh, it's crashed. Oh, this is exciting. Speaking of macOS, I didn't mean to badmouth you, Apple. I'm really sorry. Ooh, that went horribly wrong. And then, of course, we've got new backends like WASI, where you're trying to build these runtime interfaces in, but you have to decide how to dispatch the high-level APIs to these backends. And what is interesting about WASI that we'll see when we come to our language design is that it is firmly free of POSIX in the front end, because the basic WebAssembly interfaces in the browser essentially had no system interfaces. And then we've seen a whole bunch of innovation in things like WASI, the component model. We've had lots of talks here at the ICFP and SPLASH about this. But crucially, the emerging model is that we talk to the outside world through capabilities. That is, we declare what we want to do, we have some state that can be passed around, and then that can be used in order to access a resource. So from the backend's perspective, it's actually surprisingly easy to look at all the active capabilities and schedule the kind of things you want to do as well. And so then the WASM runtimes can decide, well, we can bypass POSIX because the applications never expect to have POSIX. And so this is a path by which we can imagine getting rid of the need for this historical 40-year-old compatibility layer and actually implementing high-performance applications. But the one golden rule to keep in mind is that at some point you do want to expose shared memory so that you don't try to build a competing scheduler that will then destroy the performance advantages that you have this way around. So we've seen that in almost all the major operating systems, there's hints of these new upcoming things. And then there's a bunch of new backends in different operating systems, of which I've only touched on a few. Doing a survey while preparing for this, I was really, really pleased to see just how much is going on. Even in the BSDs, they're not quite dead yet. They're definitely hurting a little bit now. But there's new interfaces for security management. OpenBSD has got things for sandboxing and stuff, which is, in my view, better than most things in Linux. Then we've got innovations in the bare metal side, where you can do bare metal programming using unikernels and hypervisor level management. And so every single system that I've seen has essentially moved past POSIX now as well. And so the challenge becomes not so much how do we maintain POSIX compatibility as the first thing that we do, but really about how do we go back to exploiting these things, making them ergonomic to program with, and then using that as the basis for the way that we deploy future systems, instead of the first thing that we do to say that we're going to build an amazing runtime with the greatest GC and out-of-time compiler and cherry sandboxing, and then completely throttling its potential by using these old APIs as well. And so what I'm going to talk about now is give you a brief view about how we're looking at this in OCaml. How many people here have used OCaml before? Just to give me a sense of who knows the syntax. Who's got no idea what's going on with OCaml? Amazing. There was no one, for the record, for the streaming record. Oh, I'm really pleased. So the first slide I showed you had lots of tool stacks, and I've built a lot of OCaml code in production for Zen and for Docker, and these have been a long-running kind of system. And the way that these have historically worked and the way that I've programmed using OCaml 4 and previously is that you build a system where in order to do a portable thing that could be deployed in all kinds of systems contexts, you want to abstract the operating system as much as possible. And in order to abstract the OS as much as possible, what I do is I first of all use OCaml functors, which are parameterized modules for those coming from Haskell. And they give us a bit of portability by letting us abstract across a console interface or a notion of time, so I can use different timer sources. And then in order to begin a function, I pass in an existential that tells me that I have a capability to use this hardware. In this case, this C is a console first-class module that corresponds to this this first-class module here. And then in order to then block, I use monadic concurrency, which is a user space library that just says, run this thing after this thing, using LWT for those familiar with it as well. So this has been a very classic way to program, and I've very happily written quite a few hundreds of lines of code that work this way. But then there's a whole bunch of problems with that, because ideally it is a bit verbose when it comes down to it. And so the thing that we've done new is to develop a new feature in OCaml 5 where we can make this happen. We can just begin something called EIO main, and then I can run using a direct style control flow, and I've actually removed a huge amount of the boilerplate. No more functors. Capabilities are passed in through a mechanism that is very subtyping friendly, and then it's direct style blocking. The semicolon is back in OCaml. And we can use imperative affordances, because it's really nice having for loops in OCaml, right? And having to rewrite everything in a recursive style using monads just got a bit tedious after a while, and lots of syntax extensions came up. So the direction of travel here in OCaml 5 is to say, well, we can rewrite a bunch of code. We can use subtyping and a new feature, which I'll explain next, in order to make this happen. How many of you here have played with OCaml 5's effects? So, oh, interesting. So while almost all of you knew what OCaml was, OCaml 5 has had a new feature, which I'll explain next. Only about a quarter of you have seen this one before. And what this lets us do is that it lets us, in user space, define resumable continuations. And resumable continuations mean that we can, resumable exceptions, which have a continuation in order to do the resumption. And it lets us write code like this, where I can define a function called fork, which can block internally, and then I can do another fork, and then I can even do message passing between these two functions through this exchange thing, and no monadic concurrency is required. So we can write in user space, using these new effect handlers, all of the logic required to implement this particular thing. And this is an example from the OCaml 5 manual. So if you want to play with this yourself, I highly encourage just going to the manual and reading the examples that Casey Sivaramakrishnan wrote for that. And how it looks is this, to give you a quick sketch. First of all, you write down the name of the effect, and we have an extensible GADT for all of the effects. So in this case, we define two new effects, one called fork, which takes a function, and another one called yield, which just stops. And then we define convenience functions here just to perform the effects. So at this point, this fork will go off and raise this effect, and the effect has to be handled somewhere. So the handler is quite fun. So in this case, we built a very trivial fiber system where we have a run function. And notice here, again, the lack of any monads. And we define an exchanger, which is just where we're going to store our message passing buffer. Then we can enqueue things by putting them in a normal queue. Except here, now we have something called continue, which can resume a continuation that's passed in. And where does this continuation come from? Well, this comes from the effect handlers. So whenever you spawn something, you can then get a result from the function as normal, at which point we finish the fiber. You can get an exception, at which point you just raise the exception and you dequeue it. So I haven't shown us re-raising the exception, but that's probably what you would do. But we can also now pattern match something called an effect. And what the effect does is that it like an exception, it has the exception value, but it also comes with a continuation that lets you resume the function at the point that the exception was raised. And continuations are one shot, so you must either discontinue them, it will be a memory leak if you don't, and you can only resume them once. Or there'll be a dynamic exception raised for that. And this means that it can be very, very fast. So they're almost as fast as raising an exception, a little bit more stack keeping, but not much more. And this is enough for us to then build a fiber stack in which you can run this nice direct style code that we saw here and in user space, define the scheduler that you're trying to aim for as well. And this is a secret for how we can support all of these new I/O backends. And so the thing we learned in about 20 years of OCaml coding is that there's loads of really cool things about OCaml, right? It doesn't force you to do things. It's got a strict execution model. It's got run loops that you can customize. It's the perfect language for systems programming in many ways. Except that handling I/O was really painful because you have all these monads, you have lots of heap allocation, you lose your backtraces, and after a while, debugging that really becomes a drag. And so what we're trying to do here with this new modern I/O library is to help us to match the impedances from these systems where we've got all these shared memory protocols and make them run as fast and as ergonomically while maintaining the programming affordances that we need. So I want my backtraces, right? When I'm looking at a production a backtrace from Docker from a very, very grumpy customer. And the way this works is that you essentially have to think about I/O in the modern runtime as being a DSL from the mutator that is interpreted by the backend. And so if you think about, at a very high level, a mutator in a runtime is waiting for I/O. So it's got a data dependency graph of I/O it needs. And then on the other side, you've got a bunch of I/O being produced by some other side, and that's also got its own data dependency graphs. You're trying to match these graphs. And the faster you can make these graphs more bipartite, then the more you can just proceed and make progress. And the more you have to rearrange the graph, the slower you get, because that's just time that you're not processing the graph. And so in EIO, we have a bunch of high-level functions that try to, as declaratively as possible, manage I/O without specifying exactly how to manage it. So in the old days, if I wanted to copy a buffer, I might just create a buffer, copy, read a magic number in here, and then output it to stdout. And now what we do is in EIO, we say, well, give me a flow to copy and define input and output flows instead. And then the backend can decide how to spawn the fibers, to manage all the shared memory queues, because it's got a notion of user-level concurrency that has been defined by the application. And therefore, then the OCaml runtime can go off and decide how to keep its shared memory buffers full, which then propagate all the way down the stack as well. It's good at a high level. It has been really interesting in EIO, experimenting with writing front ends and back ends to all of the different pieces. A lot of this work has been done by Patrick Ferris and Thomas Leonard, where initially I just set the challenge out saying, well, let's just build an IO ring backend, because that was the most obvious one. And then we had the POSIX backend as well, but it's kind of a second-class citizen. You have to use POSIX sometimes because IO ring isn't quite complete yet. And then we've ended up with macOS, where it just doesn't work because of all of the Garand settled dispatch. So we're still trying to figure out exactly how to map the runtime to the fact that the kernel might decide to move CPUs and so on. It's possible, but it's going to be a bit slow and messy. But it'll be stable. And then we have Windows, where it looks near perfect because of the amazing amount of asynchrony there. And Windows has always been painful because its POSIX backend isn't really POSIX at all. And there's lots of translation layers to make that work over the last kind of 20 years in OCaml, heroically maintained by David Alsop. But now with these new backends, David is getting excited again by the prospect of writing IO code, because it could potentially be the best backend for OCaml anywhere. And BSC is kind of being left behind at the moment because it's still got to use a POSIX backend, but POSIX does still work. It'll just be a bit slow. And then we have exciting new backends. In JavaScript, you can choose to use a higher level API. And then in unikernel backends, you can decide exactly how to dispatch the I/O, because you have full control in the backend as well about how you manage I/O. So all we do is that in our low-level interfaces, we expose each of these individual libraries that give you the greatest, lowest level non-scheduling interface towards these low-level interfaces, and then we provide high-level interfaces that are more declarative and managed using the effect system in order to do dispatch as well as possible to the most native API available in the operating system. And only if that doesn't work does it fall back to POSIX, and it'll operate more slowly. So just to give you a sense of what it looks like, it's super fun binding shared memory protocols, super dangerous and super fun. We have type-safe bindings to IO ring in Linux, where you can use nice OCaml combinators to do the lifetime management. So here, I'm just managing the heap. One of the really nice things about the U-ring bindings is that user data I mentioned that you push onto the queue into the kernel is the continuation of the fiber. And so the only thing that the runtime has to do, apart from a tiny bit of bookkeeping, is just to basically jump to that continuation, and it's in the OCaml runtime. So the amount of bookwork from some I/O event completing in the kernel to being in the mutator is extraordinarily small. And this was not the case with using historical backends like select and poll, where as you saw in the syscall trace, you have to do a lot of work in the runtime. So it's refreshingly small and simple. And then while there is a certain amount of dynamic lifetime management, there are further advanced extensions to OCaml coming up now, such as OxCaml. You would have seen that in the Jane Street booth, where we have the prospect of doing more lifetime management at the type level. And so therefore, the direction of travel of this is one of safety eventually, even if there's some dynamicity in it right now. And then the high-level interface is looking very much like WASI and like WebAssembly, where we have capabilities exposed as the default programming model for everything we do in AIO. So you can do things like you have a standard environment that is using object types, which are really syntactically convenient in OCaml, even if they're much maligned. I'm a big fan. Because you can ergonomically subtype them to say that I just need these parts of my environment in order to make progress. So stood-in, for example, is just an object type of a source where it only has a stood-in function, and then you can have all kinds of interfaces exposed using this subtyping-friendly interface as well. And then just to give you a hint, also you should go off and look at the EIO documentation to get a full sense of it. It's actually really nice when doing systems programming because the type gives you a lot of information about the resources you need to access. It seems kind of obvious, but we just haven't had that in the way that we program all of this time, right? When you look at a function now, I can see that my certificate management here requires a network interface in order to do something. It doesn't say what. And you can, in user space, further refine these to do more application-specific capabilities. Whenever we're reading things from disk, we always take in an environment, and this environment then allows the system to use the best sandboxing-friendly APIs available, and then this is all enough for us to proceed and then dispatch them to the back end, where POSIX simply does not have the right security primitives to make these things work well, but we know that Linux does, and so therefore we use the best-of-breed APIs for that platform. The ultimate goal is that when you look at a trace of operations from your application to your runtime, to your kernel, to your hardware, it should be as if you've handwritten it, right? If you knew exactly what you were doing and you knew exactly what the stack was, how can we get as close to that as possible and as aligned as possible without any kind of magical programming? And this is obviously not perfect yet, but it's getting us in that direction because we can unlock the ability to use modern kind of I/O backends, and then we can focus our attention next on memory management and lifetimes and all the other things that we need to also worry about as well. So I've given you a bit of a whirlwind tour into sort of where we've been going with all these backends, and I just wanted to recap some of the high-level points for you as designers and implementers and users of managed runtimes. The first thing is that try to make your managed runtime not block. Just don't stop if you want to go fast. Seems like a good training trick. And so recognize that there are shared memory channels all the way through the stack. Use them and make them easier to share. So isolation is easy to do in an operating system. You just turn the thing off. Safe sharing is really what makes operating system design really hard, because you have to define what safe means and what sharing means and how long it's going to happen. And so this is really the core API challenge behind, I think, exposing these new APIs. And just remember that POSIX, if you ever see it, will basically slow you down, but it's still around causing trouble because it's still the back end. So just treat it as the second thing that you work on and not the first thing, and then it'll help you kind of focus your design minds on exactly how things are going to work. And so while this is true for Linux and Windows, macOS remains awkward. And so I think an active research area that would be really interesting is trying to figure out exactly what lies between the shared queue model of macOS and the lower level shared memory rings. It should entirely be possible, for example, to build an MN queuing concurrent model on top of the lower level APIs, but to my knowledge, it hasn't been done yet. So libdispatch and Swift have been ported to Linux, but not in the kind of high-performer way I would have expected, presumably because it's not a very popular deployment target. But there exists the ability to do these things, or to do them within a managed runtime as well. And if you want to experiment with these things, EIO is by no means a perfect library, but it's what I use day-to-day in OCaml programming today for doing my day-to-day work on planetary computing. So I process petabytes of data using this thing. It hasn't crashed. It's been pretty ergonomic. I've been a happy user because it exposes primitives for zero-copy memory. It's got higher-level interfaces that don't take advantage of all of the backends yet, But as we write more code, we're getting familiar with where to plug in these optimization passes, and the use of capabilities has been really refreshing. Like, it's caught genuine bugs in code where the wrong file system directory is being opened, that kind of stuff. And it just gives you another level of hygiene, which we should all be using in the modern day as well. So it's definitely very much a Wild West. I hope I've convinced you that I/O research can be fun. You have to have a problem that demands this, and so I encourage you to find problems where you've got lots of data and latency requirements and interactivity, and then just dive in and experiment with some of these backends and start sharing information and knowledge about how to pull that off as well. So with that, I'll conclude, and I'd be happy to take any questions you might have. Thank you.
Yeah, thank you for the great talk. So we still have 10 minutes for questions. So if you have questions, please make a queue in front of the microphone.
So great talk, thank you. So it seems like IOU ring is kind of a response to two things being expensive. One is system calls being expensive because of privilege changing, and also threads being expensive.
Yep.
So I'm wondering, so you didn't mention Go at all, and Go's concurrency model. I'm curious if there's something about that that you could think about also in this space.
That's a great question. I've never had good experiences with the Go concurrency model after doing a lot of Go in Docker, mainly because we found that we had to avoid the first-class concurrency primitives in order to get high performance in Go. So you generally don't want to use lots of Go routines if you want high performance Go. And so we ended up in systems code of essentially de-Go routining the code and ending up with surprisingly low-level code to make that work. So I view Go routines a lot like using standard ML style synchronization because it couples up synchronization with communication. And I do think an essential point of all of these shared memory rings is that you want to decouple synchronization from the act of communication. And so we're not coupling them in our EIO libraries. But historically in Camel, we've done the same thing as well when using standard shared memory channels. What I haven't seen is if Go has an IOU ring backend, and I'd love to investigate that more after your question. Does anyone know if Go has an IOU ring backend? Any Go programmers there? One thing I have seen is that it's surprisingly hard to retrofit IOU ring though. So Rust's Talk.io took a long time to have a U-ring backend because again, if they've coupled just enough in their previous API, it's very hard to figure out where to insert the scheduler. And that's what we have with effects in our Camel is that we have a place to shim a scheduler in that we can control at an application level as well. So perhaps that's the key difference. If Go gets user-defined effects, it might be easier to write the Go synchronization routines in Go itself.
Yeah, just a final comment on that. It also seems like you have to be a Go expert to be in the Go runtime. Like it's not like you can go and modify the Go runtime easily as a non-core developer.
That's right. A lot of this was inspired by, I think, Casey Silver and Christian. He interned with Simon PJ, the Simon & Simons in Haskell 2013 or something, and he wrote a user space Haskell scheduler for their really fancy runtime then. And that's really what inspired all this work because we're like, well, why don't we do this in a Camel? We have to make it multi-core, so we might as well write these things as well. So, and then happily, the IO backends all kind of, accelerated, so everything's converged at the right time. But you're right. The EIO backend is subtle and quick to anger, so it's not something you want to casually modify, but it's something you can modify without having to recompile your language. I think that's important.
Thanks.
Thanks, Ben.
Hi, Neil. Thanks for a very stimulating talk. I have a comment that I think I can make into a question at the end. The comment is that POSIX is my semicolon. So in the middle of your talk, you said, oh no, Camel, actually, it's nice to have semicolons. We have these affordances that we like, right? And that's the way I think about POSIX, right? So you spend a lot of the talk basically saying POSIX bad, you should hate POSIX. I mean, you didn't quite say that. But actually, nothing in POSIX is opposed to having shared memory interfaces on the side, right? So I suppose, how do you reconcile these two attitudes? I feel like I could go on about how, more and more asynchrony isn't necessarily a globally good thing, right?
Yeah.
So I don't know if you, I think I finished my comment without actually asking a question. How do you reconcile those two ways of looking at the world?
Stephen, I will reconcile that by crossing the line and giving you a giant POSIX hug because you're completely right. When booting an operating system, when doing interactive debugging, there's all kinds of reasons why you want to do that, right? So if you think about a lifetime of a computer, there's a boot process, there's a configuration process, and there's a go leave it for 10 years process where you just want to do things. The boot process, the configuration process, all of that should be, a nice, simple, synchronous API. when you want to make it go fast, you then want to leave it alone, and that's where you want to activate all this stuff in. So POSIX is a wonderful place to do configuration and mess around with things. And so is the browser as well, in a different way. And so if we phase these things right, then everything will find its time and place. And I'm definitely not saying get rid of POSIX, but I am saying if the steady state purpose of a runtime is to process exabytes of data potentially over the lifetime of the process, then you should design first with that data flow, and then everything else should come around that and make it ergonomic. And that's where I see POSIX fitting into all this as well. But I'm a huge fan of extending POSIX, and I wish there was a way to reconcile these two things. One of the concerns here is that we don't have a POSIX-like process that helps to bring these things together. So the Windows URING and the IO URING backends are subtly different in terms of their metadata. They expose a lot of the kernel. We've seen the security issues. So if anyone's motivated, and I'm looking directly at you now, it's actually a great time to try to define the semantics of what POSIX 2026 looks like. That is a departure from that. Maybe give it a new name. And in fact, if anyone wants to chat about that here, it feels like a good place to discuss this over drinks. Thanks. So thank you for that comment.
Hi, wonderful talk. I've also had some. I've also tried out EIO, and I found it pretty ergonomic.
Oh, good.
But I also wanted to ask about, so here in this case, you decided to say, okay, IO URING is something that is worth kind of keeping, so we're gonna build like a abstraction over it, and we're gonna expose it to more, I guess, more general audience who doesn't maybe know as much about like the low-level API. But there's also things like ePOL, which never really took off. So how do we as language implementers know which features are worth supporting abstractions for, and which features we can kind of skip out on?
It's a great question. So there is, to quickly recount the history of FT synchronization, you've got POL, PPOL, KQ, ePOL, URING. There's quite a few of them. They're all different, right? So they all, Select, obviously, I forgot my old friend Select. They're all different because some are edge triggered, some are level triggered. Some have different scalability, some have dynamically sized in terms of the number of FTs you have. So you really have to size. It's very hard to build a runtime where you don't know what the deployments are going to be. And I think one of the points of URING is that it's actually quite feature extensible. So if you know that you're going to be running on an embedded device, you're probably going to go for a simple polling style interface, because that's ultimately, you don't need to have 1 million FTs. The problem really arises when you don't know where your runtime is going to run, right? And that's often been the case with things like Docker and Zen and things where people just deploy them in unexpected ways. So one of the things I've been thinking about in URING is that you can actually write a shared memory proxy in user space that can translate to all of these other APIs pretty well. So one thing that might be worth investigating in runtime is to say, make it shared memory first, and then you dispatch by processing in an internal thread in your runtime to one of these kind of backends if that's the only thing available. That's kind of effectively what EIO does, but in a slightly roundabout way. But you can also then make this a first-class citizen, right? You can translate between language runtimes if you wanted to. Because shared memory, it's a network protocol that can't go over the network, but it can go across cores and across different parts of the machine. So if I had to build a multi-language interoperability story, I would do it over URING now, because that would cover the full set of RPCs you would need to do across the runtimes, and then put an internal translation in, for example, to Go or anything else as well. So it doesn't quite answer your question, but it's really about how much extensibility you want. And I think that's when you want to look at these new things. I'd be very cautious about making URING the default runtime only, given the, you really need a modern Linux today, and this is really a direction of travel. So you have to get familiar with all the APIs, unfortunately, right now. But if it come back in 5 years, it might be a different case. It's just, these things take time to migrate.
Sounds great. Thank you.
Thank you.
Hello, thank you for the talk. Very, very nice, very
I'm glad.
interesting. Polybos Pratikakis from University of Crete. We are using a combination of memory map and I/O to basically use devices as memory, as parts of the memory hierarchy. How are these faster ways working with memory map? Can you still use memory map as your safety net and then use as I/O to accelerate?
Right. It's a great question. So the question is essentially, once you have memory, how do you manage that memory? So the short story is that this tower continues up and it continues down. And so in the hardware, there's a bunch of synchronization built in for different types of memory. And usually this happens at the hardware level, right? So it does cache coherent synchronization. But then when you have different types of memory, like network memory or GPU memory, you've got a bunch of protocols which are increasingly exposed to user space in order to manage them. So this is particularly true for GPUs, where most of modern systems programming is tensor networking, right, to GPUs. And so you've got things like NVLink and ways to manage all these cards. There's probably around 15 to 20 kind of widely deployed APIs at different levels of stack, all the way from InfiniBand and RDMA to various forms of persistent memory, which have now been canceled, like Octane, and then all of the GPU and FPGA interconnects as well. So it is an open question saying, how do you, we could in theory write protocols for each of these low-level drivers and do exactly what I described here. I haven't done that yet. I'm not quite masochist enough, I think. It's just, you have to have a very specific problem to make that happen. But a lot of this does happen in operating systems and hypervisors today. So if I look at the Zen evolution today, there's specific kind of backends to do with memory mapping metadata, which is where you shove all this. So normally a page is readable or writable or executable. Now there's many, many more things that tell you about the coherence of the memory. Is it write through, where it'll go, the source and destination, and also generally what the alignment requirements are, for.
So they do work together.
It does work, but it's an extremely manual process right now. And we're really hampered by the fact that NVIDIA doesn't export, it doesn't have a good open source story at all. Right? So the documentation joke I made is really quite true. We just have to reverse engineering all of these pieces.
Well, I was thinking of storage, not GPU.
Oh, so storage is really interesting. There's a bunch of new products where the flash chips can be programmed directly, and they have got their own kind of flash local memory, and they have FPGAs on them as well. And so
the page table will follow the Uring.
No, they do not follow the Uring thing, because those tend to have more of a they have a tiny operating system essentially running on there. So you've got a little bit of memory, you've got the flash chips, you've got a protocol to write to the flash chips, and you've got a tiny amount of FPGA local memory to make that work. So think of it as a different operating system. And then you've got thousands of them. And then your job with Uring is to dispatch the right parts of the storage in order, so you've got to build a file system or some abstraction on top of that as well. So you need to know what it is you're building. So if you're building a vector store, for example, with lots of sparseness, then you define the hash function in user space, and then you dispatch the function. So in theory, you could build that with the I/O. We just haven't, but it'll be a really fun exercise to do that as well.
Thanks.
Good. Thanks.
Thanks so much.
Yeah. Thank you, everyone. That was wonderful.
Thanks for the great talk. Okay, so where's the next speaker? Okay, next is the final presentation in this session. The next talk is presented by Yulong. The title is TIL, a Total Expressive Assembly Language.
Okay.
Please.
Yeah. All right. Hello, everyone. Today I'm talking about teal. I don't know how the color looks like, but it doesn't look like teal to me. That's a mistake. But so, yeah. But today I'm not going to, just like a clarification. I'm not going to talk about anything concrete. This is more of a programming language talk instead of a kind of actual implementation talk. There will be no implementation. I'm just going to share a very simple but hopefully effective idea. So the scope of this talk is that we're thinking about type preserving compilation from a simply typed source language to some kind of typed target language. And the kind of problem, the kind of idea I'm trying to introduce solves the problem that how do I know what behavior is my compiled target code, and how do I verify that if I have some sophistication after compilation. So I was a little bit worried that maybe we're full of like implementers here, so people might be scared of these weird symbols, whatever they means. But I suppose the general ICFP crowd are usually fine with the typing rules of STLCs, and we'll see more of that. So for those who are not familiar, this gamma is a context for variables, and yeah, I don't think I need to explain more. So that's the source language we're considering, and the target language we'll be thinking about instructions for a SCCD abstract machine, which of course, needs to be explained a bit more. So the instructions are, we have a very small and simple instruction set for manipulating over a stack machine. We have you can push things, literals on the stack. You can pop thing. You can access copy elements from a runtime environment. You can, this is a very primitive one, so you're allowed to push a closure of instructions and code, instructions and data on the stack. You can do application, return, sequence things. And the values this abstract machine manipulates are, constants and, like I said, a closure of some instruction and a list of values. And the name SCCD machine, it's a very old name from a paper by Landing, I think. And it stands for the 4 basic components of the machine, with the C here is the control, which is the rest of instructions I will execute. And the E here is a runtime environment, which this var would copy from. This S is a stack of intermediate computations, and this D is stand for dump. I think the more modern concept is that it's a stack of function call frames, which is a list of this triple that is the saved data from a function. It's data saved when you do a function call. So I'm still going through what is the shape of my abstract machine. So it has a certain operational semantics that you just look at what is the top instruction, and then you perform the corresponding operation. For example, if the instruction is var of x, then I just find x in the environment, I push it on the stack, and I move on. If it's pop, then and the stack has the certain shape, I throw away this v here and move on, etc. And a few interesting things happens when you have these closures. So when I push a closure, then I create a closure with this code and the environment, and I move on. And when I do some application of a closure to a value, what I do is I save, the current information, and I push them on the call frame, and then I load the instruction, the environment, and the input on my machine. So that's a very a simple model of execution. But the interesting thing is we are able to type the instructions like we type the source language using the exact same types. And this is the kind of judgment I want to write. So it says that if this judgment holds, then the instruction I transforms a stack from delta to a stack of types delta prime under the runtime environments of types gamma. So the simplest example is probably this one. So what is the type of var x, variable access? Well, it just turns some stack to a stack with something of type A on it. The same goes for application. So if I have a function, I have an input, I get an output there. And the same goes for push closure, which I get a function on the stack. So that's the kind of picture I'm having right now. But like I said, the problem is given a very sometimes a complicated instruction sequence, maybe a compiled target code, how do you know its behavior? Well, we can obviously know what is the type of this massive instruction by verifying the argument, verifying the judgment. And we do this by kind of a step-by-step simulation on what is the shape of the stack. So first, I suppose the stack is empty, and then I fetch variable x here, so now it has some natural number on top. And then I get another natural number by fetching a variable. I multiply them together, I get one net now, and this goes on until we reach the very end, and we can conclude that this guy has type net. But the problem is, in many cases, you might want to verify that your target code is not only well typed, but when it runs, it will execute exactly this kind of computation. And if you're a human, if you're doing an exam question, then what you do is you just simulate the program. So you kind of produce an abstract trace of what's going on the stack. And this is essentially the same as the typing rule that I just show you. First I get x, then I get 2 x's, I multiply them together, and all the way down until I reach the final result, and maybe then I compare this to the specification I want. So this very simple idea I want to introduce today is that this process is like fully automatable, and we can just write them as the typing rules. So this is the like a more precisely version of the type system, and where I say that now my type judgment does not just describe what is how the type of the stack transits, but what value on the stack becomes. So here the sigma are a list of well-typed terms of the source language, and then typing judgment says that I transform the stack of content sigma to something content sigma prime, and the idea is that my typing judgment would model the computation just like what we did in this example here, much like maybe an abstract interpreter if you want. So now the modified instructions are all quite obvious. So well, this should be a variable, but I wrote pop here, but well, when you're popping an item, then this item is gone. That's it. When you're doing some application with two items on there, then you get one item, which is the result of the application. And when you're pushing a closure, that kind of returns E in the context with extended with X of type A, then you're essentially, the computation you want is pushing a lambda abstraction right there. So that's the general idea. And you might discover that we can do much more than just typing the instructions, but we can also type the entire structure of the machine. So we can type the runtime values, which are just base value, close values of the language, and then we can also give judgments for the environment and the stack, saying that when is an environment implements a stack of shape gamma, and when is a stack implements an abstract stack sigma with respect to some kind of well-formed environment. And finally, we can combine all of these to say that we have a kind of well-formedness judgment for all the machine states. Well, for machine states. But what does this? Why do I do this? What does it give me? So first of all, as a standard requirement for these type systems, it gives us type safety that well-typed programs will step, and it will, if a well-typed program steps, the result is still well-typed. So we get so well-typed programs remain well-typed, and it won't go wrong. But the much better thing we get from type safety with this kind of refined type system is something I call a partial correctness. So to realize that, I should introduce a little bit of the prerequisites. First of all, we can treat a well-typed environment as a closing substitution, which means that it takes, if you apply this substitution, you can turn an open term to a closed term. And then the well-typed stacks are defined to have this certain property, such that if I have these values, the judgment says that these values, v1 to vn, implements these abstract terms e1 to en. Then, applying the closing substitution of any one of these values to the environment, the result would be equivalent to the implementing value. And finally, I define that a configuration halts if eventually steps into the instruction is returned. There's a return value on the top, and there's no remaining frames to execute. So with all of these combined, we know that if we have a well-typed program that is closed and requires nothing to start, such that the initial state with the initialized state where everything's empty, this configuration terminates, then we get the final state must be in this form, such that the result state is well formed, and in particular, this stack is well typed, which means that we will have the situation that the stack implements this kind of closed value v. The result v prime implements the closed value v, which implies that they are equivalent in some sense. So to be a bit more to give you more intuition, it means that not only well-typed programs will not go wrong, it will always perform as you specify by the types if they terminate. So that's I think, a very nice property. And what if all of my programs terminate? And indeed, in this case, all of the well-typed, SCCD programs, I can show that they all halt. And therefore, with these type safety and termination combined, we get a very strong property, which I call the total correctness, such that if a program is well-typed, then executing it will not just halt, but produce a value that meets its specification at the type level. So that's the whole idea. That's the idea. You can make your type annotations a bit more specific. It's so specific that it models the kind of expected computation of your code. And eventually you'll get this very strong guarantee that all of your well-typed programs will perform as specified. All right, guess I'm approaching the end, and so make some final remarks. In the submitted abstract, we've considered a slightly more complicated calculus without the code instructions on the stack, and we have like recursors for natural numbers, which is a lot more expressive than the simplified version I introduced here. But this general idea still applies, and we still have the total correctness, and we kind of require this termination thing to be a crucial aspect, which might sound like a limitation to the expressiveness, but I think termination is quite crucial in certain systems. For example, the eBPF language, you require termination for kernel safety because it wants you to inject code into the kernel. And of course, this if you want to extend this to dependent type theory, then termination is kind of required for decidability of type checking. And so the message here isn't really that we should implement this language I introduced in particular, but we could consider this idea and maybe look at some other type theories with maybe polymorphic types, effects, or even some gradings and quantitative type theory on the types. So, yep. And here's also a link to the extended abstract that I submitted. Thank you.
Yeah, thanks for the talk. Questions?
Thank you for the great talk. So what's your connection of your work to symbolic execution?
Yes. So, could you repeat it with?
What's the connection of your work of such type system to symbolic execution?
Yes, I think it's maybe it's the same concept, but so currently we are kind of limited to the definition of equalities. For example, I suppose in symbolic executions you might have some algebraic properties, like you can equate x plus y with y plus x, but or you can do some more sophisticated simplifications. But so this one doesn't really consider it yet, but I think it could be used as an extension to incorporate both. Yeah.
Thank you.
Hi, I'm Al Ahmed, Northeastern University. So how exactly do you prove termination for SCCD? In particular, I assume that untyped programs can
Indeed,
be non-terminated.
You're exactly. Well, the magical two words, logical relations.
Okay.
Yes, so I define a logical relation over the well-typed values, and which for base types they're always true, and for function types I have to say that. So I derived this from by orthogonality standard, but essentially it says that if a closure of a function type is in the halt if for all instruction sequences that halts given some input, no, hold on. Well, I can write this to you afterwards.
Assuming your
yes.
inputs are terminating, your outputs will be terminating.
Yes,
basically.
yes.
Right? So the trick is that the only types you have for SECD are base types and function types?
Indeed.
Okay, perfect. Yeah.
Yep.
So basically it effectively models STLC.
Exactly.
Okay.
Yes.
Thanks. Any other questions? Okay, thanks so much.
Okay, thank you.
Yeah. And our next talk is in about 50 minutes. Sure.
Hello. Is it Microsoft?
Sorry?
One. It doesn't work.
What do you mean doesn't work?
Okay. Hello.
Just a little quiet, it always has been.
Okay.
Yeah, the live stream can hear you, and I think the room can hear you.
Okay.
You asked me if you wanted, because I normally have it muted. I just unmuted it because I thought someone was announced soon.
Okay.
Yeah. Yeah, I try to basically unmute it as the presentation is ending or different transition points. I learned my lesson, otherwise it's just muted if the organizer starts speaking. Otherwise it will often be muted if you want, if you're not sure. Just
Yes. Okay. Well, hello everyone. I hope to hear me. I am Iakovos Kolokasis. I'm going to chair this session now. We're going to start with the presentation of the research paper Matza Race Detection in Java. Polivios Pratikakis, who is a professor in the University of Crete, is going to present us this paper. Yeah.
Okay, thank you. Hi. This is work done primarily by Alexandros, who was a student at the University of Crete and who sadly could not be here today because he just started his PhD and had to move to the US. Also work done together with Iakovos, Fivos from Red Hat, and Angelos Bilas and me, who are both faculty at the University of Crete. So, what is the problem here? We are trying to find data races in Java parallel programs. And data races are difficult to find, and there are many tools that try to find races, both statically and dynamically. And these, the problem and the issue with the existing tools at this point is that many or most have a problem in terms of practicality and how to deploy in a production setting. Things that can go wrong are, for static tools that try to usually be sound, are the false positive generation. So for every data race, you have to analyze hundreds and sometimes even thousands of warnings, right? Also, static tools have the drawback that you need the whole program to analyze, and the analysis of big production-grade codes might involve hundreds of thousands or millions of lines, and static analysis might not scale. But one other thing we found that is a problem for both static tools and dynamic tools that do instrumentation statically is that many of these production codes generate and then load Java bytecode on the fly. So you have code that produces Java bytecode and then loads it and runs it, and this is very difficult to either analyze statically or annotate statically. The other thing that's a problem with dynamic tools is performance, because most of these dynamic tools usually run Java in the interpreted mode, and that is all well if you're running small programs, but if you want to run either a big program or your program with a huge data set and a long execution, then running in interpreted mode is not very practical. The other final issue that you might have is that the current state of the art is usually some sort of algorithm or analysis or tool that's been ported to Java from a different language. The main competitor here is the thread sanitizer, right? And there are issues with the Java memory model and the Java concurrency spec that you might not get. So the objective of this work is we want to build a dynamic race detector, and we want to build it specifically for Java, and we want it to be very practical. So we want to be inside the OpenJDK, And by inside the OpenJDK, I mean we want it to be very fast, so we need full JIT support, make hotspot work. We want to work with garbage collection and hopefully with all garbage collectors that you get in the JVM. And we want to handle the semantics correctly for the Java memory model, the JMM. And then hopefully will give you less false negatives, so you don't miss any races, and you get better support for things that will go in reality. The other goal was to generate output that is very, very useful for debugging. So you cannot just point at this memory location. You get 0x, FFFF, ABCD, and that's your race warning. That's not very helpful if you're a Java developer, right? So you want to translate things back into source lines and stack traces. Okay. And we want to run real stuff, large applications, large data sets, large codes. So what we did is we built this tool called Matcha. And here, the name is the closest we could get to paying tribute to the thread sanitizer, Tisan. And Tisan, if you spell it a different way, is a kind of herbal tea, right? So again, if you pronounce this wrong, it's matcha, which is another kind of tea, except ours is with caffeine, so it goes faster. And the idea is we implement the fast track algorithm like the thread sanitizer, the same idea with vector clocks, a bit differently so that we capture the Java nuance. We integrate this into OpenJDK. We support JIT, all the JIT compilers in the JDK. We track all kinds of memory accesses that matter and can produce races. And so this counts a lot for performance, because the Java memory model helps you get rid of some things that you would have to instrument otherwise. And we have a novel technique for producing better race warnings, so we can reconstruct the stack when something goes wrong. We compare against the thread sanitizer, the current state of the art, and we do an experimental evaluation on a set of small benchmarks so that we can compare, and then sets of benchmarks that at this point no other tool can run. We found races, we found unknown races, and some of them have been fixed in the repositories upstream. And so I'm going to give you a small summary of how this algorithm works. This is not our idea, this is the algorithm used also by thread sanitizer, right? So we want to detect what happens before what, and by extension, what could happen in parallel, and thus is a race. Let's say you have two threads, and we give every thread a vector clock. And here, every thread has a vector clock where the first location is the clock that I know of. Let's say I'm thread 1. Thread 1 is at clock 0, and thread 1 knows that thread 2 is also at clock 0. And then thread 2 has a similar vector clock. Its own time is 0, and it knows about thread 1 that is also 0. Right? So every thread has a vector of clocks capturing what they know about the other threads. And then we put a vector clock also in every lock, and by extension, I'm going to extrapolate to every other synchronization mechanism that you might have. And then every time a thread does something of relevance, it advances its clock, right? So thread 1 is now at clock 1, at time 1. And then maybe thread 2 advances its clock, right? And so every thread can observe some notion of time. But then when you lock and you acquire the lock, the clocks are synchronized. We're going to pull whatever the lock has captured from the other threads and put it in thread 1. In this example, there's nothing. But then when the other thread is going to try and get the lock, it's going to block and get the lock as soon as it's released by the first thread. On release, you get the time from thread 1 and you save it in the lock. So what the threads communicate to each other is basically what do you know about where everyone else is? And this is done through the logs. So we take the vector from thread 1 and we save it. We add it to whatever is stored in the log. This is the information. This log now knows that thread 1 has advanced at least up to that point. And then when the log gets locked by thread 2 is going to find that out. So now thread 2 knows via the log that thread 1 has advanced at least up until time 1. Everything that's happened in thread 1 up until time 1, now thread 2 knows that it's happened. So we say that's everything that has happened in thread 1 up until that release has happened before everything that's going to happen in thread 2 from that acquire on. And so this gives us a way to detect this happens before relationship. Okay, and using this happens before relationship, we can figure out if two accesses can happen at the same time and then flag a race. So on every access, if we have this happens before relationship, what you need to do is log somewhere what thread did the access, which memory location, right? Was this a read or was it a write? What time? Stuff like this. And then with this information, every time there's a subsequent access, you can compare with the last accesses that you've logged and figure out, oh, there's somebody that has not happened before me, so it could happen in parallel. The clocks are not necessarily larger or necessarily smaller from each other, and thus these two accesses can race, and so you can flag a race warning. And so this is the algorithm, the fast track algorithm. This is what TSAN uses as well, and so we are based on this. And here's where the differences start. We want a fast representation, so we also use shadow memory. You have the Java heap, so you map it on a very, very big chunk of memory that's going to store all these access logs. But then you don't have to map every memory location in the process. Because in Java, the only thing that can be racy are field accesses, basically. Nothing on the stack can be shared. The objects, the rest of the stuff in the objects are not updatable. So there's one difference there where you can save memory and change the representation of shadow memory of what accesses you're logging. We remember the 4 last accesses, which is similar to the state of the art. And the other thing we do that's different is every time we log an access, we have a specific mechanism to also capture the minimal information so that you're fast, the minimal information that you require to rebuild the stack trace for that access, because you might discover that this access is involved in a race 2 seconds later, and that stack is going to be gone. So you have to reconstruct the stack so that you can say, this access that just happens now races with that access that happened a while ago, maybe in the next execution that you run the program, and I can reconstruct and show you the programmer a stack trace for both so that you can track the code and fight the bug better. So this is another problem that we solve specifically in this work. How can you very, very fast log the information that you need so that you can reconstruct stack traces that are gone by now so that you can produce better warnings. Okay, design points for this tool. We use a shadow memory to store the access log, plus this new thing, the stack reconstruction logs. We want to work with a garbage collector inside the JVM, and the garbage collector might change object locations, so the same thing, x.o, that would be in address 0 when your program runs, after the garbage collection might have moved to address 5, right? So you want to keep track of which accesses refer to which locations. What the people do so far is when you migrate your object with a garbage collector, you go and find the trace for all the accesses in that object and migrate those as well. And that turns out is very expensive. And it turns out, and the details are in the paper of how we measured this, that it's actually not worth it, because if you just wipe everything from the logs part of the memory, and you, every time you garbage collect, and you unmap all the memory, so you free it, you return it to the operating system, you're not going to miss many warnings, right? The garbage collector does not fire that often, especially in this setup. Okay. The other thing with garbage collection is that you will change the location of objects, which means you will change the location of locks in memory. Because in Java, every object is also a lock. There are two lock interfaces in Java, and one is the object lock. This is the implementation of the synchronized blocks and synchronized methods. Our solution to this is we embed the vector clock inside the object header, so we had to change the object header and some of the internals to make it work in OpenJDK. And so that when you move objects, the lock follows and all the vector clocks work. And this works with every garbage collector inside the OpenJDK. The other thing is this idea where you have to reconstruct the stack. And reconstructing the stack is a kind of time travel. So we want to figure out, after you pop all the stack frames and you do something else, that I should have taken a photo of that stack. And that's what people did so far. They took a photo of the stack on every axis. And copying around all these photos is very, very expensive. So these tools used to be very slow. What we do is we have a buffer for every thread, the stack event buffer, and we just append to that buffer. So that's an immutable data structure. You start with a copy of the stack, and then every time you enter a method, you add the enter method event. Every time you exit the method, you don't pop it. You add an exit method event. Okay, so far it's just a trace. The good thing about this representation is you can restart at all times. It's very easy to restart. When your buffer is full, when you want to make some space, whatever, you just start a new buffer and you just copy the existing stack there, and then you never have to go back to the old buffer again. Okay. You can append there. So you can restart at every point very, very fast. And the other thing is, every time you log an access, all you need is a reference. I was at that index inside that buffer, and then you can walk backwards in the buffer and reconstruct the stack up to main. Okay, that's the idea. It's really a simple idea, but I don't know what nobody did it so far. So we do this, and it really, really reduces the time for managing and producing the information for the warnings. The other thing we did differently is we group all these warnings in terms of source lines. So if you have the same data race and you run this code 1,000,000 times, you don't get 1,000,000 warnings for 1,000,000 different objects. The programmer can say, you know, this is one data race that involves maybe 1,000,000 objects, but it's between this source line and that source line. Okay, so we implemented this in Hotspot in both the C1 and C2 just-in-time compilers in OpenJDK. We instrument the code in the intermediate representation for the Hotspot compilers. We instrument every read and every write that can raise. So this is not every read and every write in the whole process, right? And so this makes it faster too. Being able to JIT compile is also much faster than interpreter. Unfortunately, because you instrument almost every read and every write on a field, there are many optimizations happening in C1 and C2 that you cannot do anymore. You cannot reorder stuff very easily around. And so it's much faster than what you would get so far, but up to a point. This is not as fast as not running a race detector. Okay. The other things we do for speed is when we create this access cell, we need to check on every access the previous accesses to compare and see if there's a data race. And this, because this is a SIMD operation, basically. With some tweaking in the JIT compiler, we can take advantage of x86 vector operations and make this operation very, very fast. The final thing, the large amount of work you need to do here is instrument all custom synchronization operations. And so you have to go inside the library, Java util concurrent. This is custom locks, read-writer locks, and all that, and do the vector clock thing to find out that happens before edges. Okay, so to summarize all these differences between our tool and the state-of-the-art, we work with the full stack interpreter plus hotspot JIT compiler. We ignore synchronization that happens in volatile fields, and I'm going to explain this in a bit, instead of modeling them as synchronization. We found some issues with the Java memory model and how you treat static initializers, and I think I'm going to try and tell you very fast how this is more correct. And we have some differences in how we handle thread join. The thing with volatile fields is that people write code like this, where there's a while that's going to spin on a volatile field up until there's a thread that writes the volatile field and takes you out of the spin. And a lot of people write custom synchronization code like this, and the Java memory model allows you to synchronize like this, because the Java memory model says a write on a volatile field and a read from a volatile field will will synchronize everything else in memory, even another third place in memory that's not volatile. The problem is that you can write code without the while, and there is no dynamic analysis that can tell this is an implementation of a spin lock and that isn't. This is a race, right? And so, because people do this and it produces warnings, what dynamic tools do is basically ignore all of volatile and raise their hands up and say there's no race here, although there is. So this is the main one of the issues with Java nuance. You can find many more such issues in the paper. Okay, so we run this and we measure how fast it is, and it turns out that we are quite slower than running just the JDK, but quite faster than what people would do so far. Okay, if you can JIT compile, basically everything becomes faster. Okay, I'm a bit over. Okay, so I'm going to take a couple of minutes from the question time and to say that we also measure the memory usage, how much memory you use. And it turns out, these are gigabytes, it turns out you should be using at worst 4 times the memory than your Java heap. And this is very, very variable from application to application because of page locality, because you will always memory map 4 times your heap, but sometimes there are things in the heap that are never accessed, and so these pages are never going to materialize in the shadow heap. And the other thing here I'm going to explain is this thing. Sometimes we use less memory than even Java. In the end, we are 15 times faster than the competition. If you want to find races, we can run with heaps that are many gigabytes in size with big benchmarks. At this point, you cannot run anything with interpreter-only tools like this. And sometimes we even use less memory, but that is a side effect because when we use less memory, because there's more memory pressure, and so we're going to call the garbage collector much more often. And in some applications, this just reduces the residence set in memory. So, what doesn't work? If you write custom synchronization with volatile fields, it doesn't work. If you use synchronization from other languages, so in some of these benchmarks, you would see 100 warnings. This is because these benchmarks are written in Scala, and Scala has its own in-loc implementations. And so you have to go into the library and say, you have to synchronize the vector clocks. We sometimes opt to create false positives just so we don't miss any real races. There is this trick. Most people think the object constructor is thread local because usually new is run by one single thread and then you share the object. But sometimes inside the constructor you can lick the this pointer and that might give you a race. So basically we're going to find races that are not there so that we don't miss that. I conclude here saying that I think this is the fastest at this point, dynamic race detection for Java. We can run bigger programs than anyone else. It's native to OpenJDK. It's much faster than that because of JIT. It can be used for any language that produces Java bytecode, but it's going to take some porting to map the synchronization primitives to our system. Thank you.
Okay. Okay, thank you very much for the presentation. Yeah, we have questions. Yeah, if you want.
Support what? Volatile, yes. We do not consider them to be synchronization.
Yes.
Okay.
And I also assume that atomics would treat the same?
Yes.
Okay, I had two questions.
Because they do synchronize memory, but they do not enforce it happens before. They are not, they don't stop anybody.
So I had two questions. First, do you observe any false positive because of that?
Yes.
And second is, why exactly do you not support them? Because I feel like, for example, Trace Synthesizer supports atomics, and it can model what happens before atomics.
So the idea is, if you can use a volatile variable, like in this example, to implement a spin weight, right? And here, there's no race. You will actually make thread 1 wait until this right.
Yeah.
Okay. But there, it is a race, right? Because the access to y is not synchronized by it. And all the tools that consider volatile accesses to synchronize with each other will miss this race. So in order not to miss this race, we have to allow this false positive.
I mean, it depends where you read from dynamically. Like if you read from volatile, right? Yes, it would miss, but you can be lucky and you hit execution and it reads from different ways and you will observe the risk.
So the whole problem is that here there's no mechanism to enforce ordering between the volatile access and the volatile access, right? And this is an illusion that there's an enforced ordering here. Because Java says this volatile access and that volatile read up there on X is going to synchronize memory. So the value of Y that you read after the while is definitely going to be the value of Y that you write here. Okay. If you don't have the while and you just use a volatile variable, what the other tools that try to model this will do is you have a volatile read here and a volatile write here. And they will assume that the volatile write and the volatile read synchronize. So you will miss that this access and the other access to Y can actually happen in parallel. Right? And this is a missed race. And this is why we consider more correct to allow the false positives so that you don't miss any. Because it happens before in terms of memory, but it's not an enforced ordering. Okay.
We get to kind of talk
Okay.
whether it's
Mm. So could you, my answer would be no, because it would be akin to, can you verify automatically that this is a correct implementation of a spin lock?
Okay, but sorry, when I said instrument, I mean, could you actually use API into your own?
Yes, that's what we do.
Okay, and so this is how your instrumentation of the concurrent primitives works, I guess.
So the instrumentation itself is inside the interpreter and JIT compilers, but if you're using custom implementations, there's an API, you can do matcha.acquire, matcha.release, and then the system will know about it and treat it like a lock.
And sorry, for the last question, for all the concurrent primitives that you have, is there some sort of commonality between these concurrent primitives, and would it be like a lot of work to actually port this to, say, Kotlin versions of the same?
So the more flavors of a lock that you have, the more points you need to touch. That's the, yeah. So,
thank you for the talk. You said that your instrumentation disables a lot of compiler optimizations.
reorderings mostly, yes.
How much of the overhead of the tool do you think actually comes from the payload of the probe versus optimizations that are actually off?
So there is some measurement in the paper about the difference between C1 and C2. Sorry. No. But it's basically, you lose most of the optimization that C2 would do over C1. So our performance with C1 and C2 is more or less the same. The benefit is much less than you would get in a vanilla OpenJDK.
And also, you said you instrument every read and write, which I'm imagining is going to cause there to be a lot of...
Every read and write that could race.
That could race. Is there any strategies where you don't have to instrument?
It would be really nice if we had a static analysis that could say, you know, all of these things are contained within a stack frame. Let's say you don't need to instrument them. But we don't at this point.
And the last question.
Thank you for the talk, and I think it's a great technical contribution. And my question is about the performance evaluation. So you mentioned that you are much faster than GSAN, and compared to it, you do not support, you ignore volatile field accesses and atomic operations, while your competitor does not. So I wonder whether the performance benefits come from this ignorance or from something else.
It's from the interpreter versus JIT. Clearly, yes. If we disable our JIT, so this is our system with just interpreter, right? And you can see, right, you go from 1 minute to 30 seconds just by enabling JIT. With TSAN, it's comparable. Not always, but interpreter is interpreter.
Well, thank you again for the great talk. You can find Bolivians around in the conference for further discussion. Now we are going to a remote presentation, memory tiering in Python virtual machine. Usually is going to present us. And do we have? Okay. We can continue with the third one.
So maybe we have our recorded
Okay.
video, so let's
Okay.
If they're not,
Yes.
have you communicated with them? Are they able to join?
Okay, so I will try to communicate with the author first, and then...
Like if we have a minute, otherwise I can default to a recording, which I have.
Okay. Yes. Yes. Yes.
But in principle, if they just stream to that,
Yes.
that's correct.
Okay.
Okay, I'm going to send email to the author.
Okay. So we can continue with the last one. Yeah. Okay. Due to communication problem, we can continue with the third one, runtime save and graph database of runtime values presentation. Is the presenter here? Yeah. The presentation is going to of this work. It's a short paper. It's going to be by Matus Sulir. Yeah.
Hello?
Okay. Hello, usually.
Yeah.
Okay, we're going
I
to
can hear you.
hear your presentation. The floor is yours.
Okay. 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 Okay, I'll start then. Hello, my name is User from Virginia Tech. Today, I'm going to talk about our work in memory tiering in Python virtual machine. So this is a joint work with collaborators from Virginia Tech and Rochester Institute of Technology. And this work is also partly funded by NSF. So Python is the world's most popular programming language. It's simple and has powerful libraries. But this simplicity comes with a hidden cost. It uses a lot of memory. Python virtual machine maintains metadata such as object type and reference counting information. A simple integer in Python can take up to 28 bytes, while only 4 bytes in native languages like C or C++. This Python programming more quickly. So a typical way to solve this problem is through memory tiering. The idea is very simple. You equip a server with two types of memory. First, you have a small but very fast tier, which is usually your local DRAM. Think of this as your desk, limited within arm's reach. Then you have a much larger, cheaper, but slower tier, enabled by new technologies like CXL. This is like your cabinet, which has massive storage, but it takes a moment to retrieve things. So the goal here is to keep your frequently used or hot data on your desk and less used or cold data in the cabinet. Essentially, what we're trying to do here is to achieve a better trade-off between application performance. The goal here, of course, is to know exactly what's hot and what's cold at any given moment. So how is this problem typically solved today? There are two main approaches, but unfortunately, neither is a good fit for Python. The first approach is managed by the OS. The OS watches which memory pages are being accessed and moves them between tiers. But this has two major flaws. The first problem is one policy fits all. The OS treats all user-level applications equally and applies one tiering rule to all applications. However, this does not work well in today's cloud because different applications have different quality of service requirements. For example, some workloads are latency sensitive, while some others are memory heavy but can be purely background tasks. So it's impossible for the OS to make specific tiering configurations for these different types of applications. The second problem is when the OS tracks page hotness, it needs to sample page access bits or relies on hardware counters. Hence, it comes with a hidden trade-off between the sampling accuracy and the overhead. It's either introducing significant overhead that slows down the application or could be inaccurate, leading to poor decisions. So as you can see in this set of figure, if you increase the sampling interval or decrease the sampling granularity, although the tracing accuracy would drop, although the tracing overhead would drop, the accuracy is significantly hurt. As you can see, the boundary between the hot and cold addresses are barely distinguishable. The second tiering approach is to build tiering directly into program language runtime. These solutions are much more fine-grained that can track individual object hotness. Plus, users can make application-specific tiering configurations. This is a great idea, but the solutions that exist today are built for other languages. In JVM-based runtime, you can instrument the read and write barriers to mark an object being accessed. Python doesn't have these barriers. In C++, you can overload the smart pointers and the dereferencing operator to track every time an object is used. Like you see in this figure, the smart pointer uses the first 2 bytes as a hotness tracker. When the is dereferenced, will increment. However, the underlying implementation of Python is in C that doesn't support this feature. Essentially, the fundamental problem is Python doesn't have the program language feature to enable tracking object hotness, making it very hard to build a memory tiering system. So how did we solve this? We found a new way to infer Python object hotness by using a feature that is crucial to Python memory management, reference counting. Python uses ref count for garbage collection. It increases when a new name points to the memory object. When all references to the object are removed, the object is logically freed. Let's look at an example of how Python evaluates a simple statement, C equals to A plus B. It does this by maintaining an operand stack. During the evaluation, the object's ref count are changed. Initially, we have variables A, B, C, whose ref counts are all 1. First, A is pushed into the stack. Its ref count increments to 2. Same thing happens to B, whose ref count also increments to 2. Then A and B are popped from the stack, followed by a binary add operation to add both A and B. Note that A and B's ref count drops to 1 after popping. The evaluation result is then stored to C. When pushing into the stack, its ref count pops to 2. Finally, after the statement evaluation is finished, C's ref count drops to 1. So notice that although the ref count variables in evaluation, they did get changed during the process. So our observation is, although ref count does not directly indicate object accesses, we can observe its changing behavior to infer their hotness. Our system therefore uses this observation to track Python object hotness. We do this by reusing the existing OB ref count field. The 32 least significant bits are left for the original reference counting purpose. We make use of the 32 most significant bits to keep track of the ref count changes. However, unlike the original ref count, our MTP count only increases no matter the original ref count increases or decreases. With that, I'll present MTP. This is a C extension module built on top of C Python interpreter. Once enabled, it runs as a background C Python thread. It first performs a marking phase to obtain all Python live objects. Then it enters several consecutive sampling phases to obtain Python object reference count changes. During the sampling, we periodically predict the sampled object hotness using our inference model. After the object hotness are obtained, we enter the migration plan for data promotion and demotion. Here we use a eagerness-driven metric to calculate hot versus cold page threshold. Because the marking phase temporarily needs to block the application, we have if that is not. I will now describe each component in detail. So to start with, MTP needs to have the full scope of all interested PyObjects. The internal Python virtual machine does maintain 3 generational GC lists to detect cyclic references, where we call cyclic GC lists. Unfortunately, these lists only track container objects, for example, list, tuple, or dict. If we only sample their hotness, a large number of objects will be skipped. So we perform a marking phase to obtain all Python objects. It works by recursively traverse all Pi objects starting from the cyclic GC list like this. Once facing an iterable object, it further traces to its children object. The marking finishes until all marked objects have no children left. However, this marking phase must be stop the world, which temporarily blocks the application. So we have to mitigate the overhead as much as possible, but still maintain an acceptable tracing accuracy. So how do we do this? We found two mitigation solutions. The first one is that we're trying to minimize the number of calls to the marking. We find out that this can be inferred by observing how CPython cyclic GC behaves. We observe that when only few cyclic GC gets triggered, the number of new objects is also very low. That means it is meaningless to initiate a new marking phase. Based on that, we'll temporarily skip current marking phase when cyclic GC activity is not intensive. While this may slightly reduce marking accuracy, missed object will be detected in subsequent markings. On the contrary, if we observe a lot of cyclic GC happen between two consecutive markings, only then would we enforce a complete marking phase. The second mitigation solution is to make sure that within one marking phase, the time taken would not be unbounded. So we transcend the nested levels of the current container Pi object being traversed. And it will stop marking immediately when either of them meets the predefined threshold. As you can see in this figure, we set these two different thresholds, values with different thresholds that can control the trade-off between the marking accuracy and the overhead. The more aggressive MTP confines the threshold, the less blocking time it would take. Once MTP obtains the scope of all Pi objects, it enters several consecutive sampling phases. Here, we're trying to capture their ref change and the user hotness. So how do we train the model in offline? We collected ref changing behavior from several workloads. Then we calculate their statistic, like median, standard deviation, number of non-zero changes, and use ground truth with offline using demo, which samples OS page hotness. And we then align the Python object addresses to those page boundaries, representing the hotness of those pages, of those objects. We choose several model architectures and fit the model with the above metrics. Note that all of these are done offline, only once. Here we show the performance of our hotness prediction model. All models actually predict the object hotness pretty well. For instance, multilinear regression, or MLR, shows a 0.7 R-squared and achieves a Pearson correlation of 0.84, indicating a strong positive relationship with the actual hotness. So here we show a visualization of a hotness heat map of a matrix multiplication workload from the OS page sampling. On the right-hand side, this is the visualized heat map when we are using our prediction model, solely using the refcon changes. As you can see, they look very similar to each other. This indicates that MTP can accurately predict object hotness within Python virtual machine without sampling OS page information. MTP triggers the migration plan to move objects between tiers. To do that, it aggregates all objects' hotness inside that page. For example, a page with 3 objects hotness 3, 4, and 3 has a total hotness of 10. We maintain the page hotness information using a hotness histogram. All pages within a bucket in that histogram has the hotness ranges belonging to a range. This is the standard practice for OS-based tiering solution. Once our hotness histogram is populated, MTP needs to decide the bucket threshold between hot versus cold. Determining this threshold is relatively easy for OS-based tiering solution. Why? Normally, the total size of the pages in bucket H and above is just below the fast memory capacity. This is because OS tiering solution can see all system physical pages. However, integrating the exact scheme into MTP is infeasible, because here MTP doesn't have the global view of all system pages. So using the fast tier capacity to set this threshold doesn't make sense. To accurately determine the hot versus cold page threshold within the Python program, we introduce a new matrix called eagerness. Here, I represents a time interval. We consider three factors to calculate the eagerness: the percentage of pages currently located in fast tier, eagerness of the last level cache misses, and the eagerness of the bandwidth going to the slow tier. The eagerness of LC miss is basically the z-score of pages encountering the LC miss. A higher eagerness value indicates more fluctuations that current system deviates from the previous cycles. Eagerness bandwidth is calculated similarly. MTP uses this information to iterate through the histogram buckets, starting from index 0 and moving to the right, one step at a time, until it finds a bucket index H where the number of pages in the fast tier is the number of hotter pages in the slow tier. This initial H is considered as the most eager threshold. If we see a decreasing of the eagerness value, this means that the current hot pages are less eager for promotion compared to the previous cycles. In this case, the threshold H is moved to the left by one bucket. We also provide a simple interface for cloud providers to use our system. Once imported, mtp.start will start monitoring the current fast tier memory size. When it falls below the memory pressure, the marking phase will then start. The mask here is the memory node mask for demoting code data. The sample interval controls the interval for sampling phases. Finally, mtp.end will stop the MTP thread and freeze all metadata. As you can see, this simple API enables per Python program, even importantly, per code segment tiering control. To use it, cloud providers can integrate compared to the state-of-the-art tiering solutions TPP Memtis. MTP outperforms them significantly. For example, in A*, which is a Pathfinder graph algorithm, under which is 25%, MTP outperforms TPP for about 1.24x. This is due to OS inability to track fine-grained memory access and falsely demotes hot pages to the slow tier, causing the performance degradation by TPP. Across 33 comparisons, MTP outperforms TPP in 25 cases, AutoNuma in 30 cases, and Memtis in 15 cases. I have to admit that for some workloads, MTP doesn't always perform the best. We identify two root causes. First, MTP spends a huge amount of time during the very first marking phase, because at this time, we have no prior knowledge of the Python object scopes. Thus, it needs to perform the most exhaustive marking across all the objects. The marking time scales with the object scope. sometimes it might overshadow the migration benefit. The second overhead is that MTP interposes the object reference count changing manipulation paths. Remember, we increase the value of MTP count whenever an object ref count is increased or decreased. This step is in the critical path that adds additional CPU overhead. To summarize our work, in this project, we propose MTP, a C-Python integrated memory tiering system for Python applications. MTP infers fine-grained Python object hotness from reference counting changes without relying on OS page sampling. It utilizes existing cyclic GC module in Python VM to mark objects and reduce unnecessary overhead. To determine the hot versus cold threshold for application itself, it utilizes a eagerness by considering wants to be promoted to the fast tier. It can deliver performance that is comparable or superior than state-of-the-art OS-based methods. But most importantly, we provide customizable per application tiering opportunities. This allows the cloud providers to tailor memory management to specific QoS needs of their Python applications. This will unlock significant efficiency and performance gains in modern data centers. Thank you, and I would like to take any questions.
For this presentation. What?
Sorry, you were muted for the first 5 words.
Okay. Hello. Now you hear me use. Thank you for the great presentation. Do we have any question for use?
So I'm going to. Hello. Can you hear me? Sorry?
Your mic is live. You just haven't responded.
Okay. So right. Thanks for your talk. I'm wondering, how do you envision integrating MTP with existing Python runtime such as PyPy or other just-in-time compiler-enabled interpreters?
Okay. So your question is how to integrate MTP into native executables like NumPy or TensorFlow, right? Okay. Got it. Thanks for your question. That's a good one. Actually, our system currently only is built on top of CPython 3.10. And for PyPy or like other Python build, they probably are implemented by different, for example, different GC or different memory management module, which requires a complete different tiering solution than CPython. So we just choose the CPython because this is the world's most popular deployed distribution. But yeah, we should look for other distributions.
Okay, thanks so much. So I'm also wondering, how is the applicability to NumPy or other kind of stuff?
Okay, that's a good thing. Because as you can see, the whole scope of the MTP is only applicable to Python objects, like the object who has a PyObject header, right? So if you want to enforce MTP for other like native executions inside the Python programs, current system you cannot do that because those objects are not Py objects, so we cannot track their reference count changes, right? So one solution I can think of is to temporarily lock MTP threads, but we can use of other OS solutions while running the native executions.
Yes, I have some questions on my side. The first one is that, okay, it's good to see the memory tiering in Python runtime. It's not very obvious to me what is the problem. I mean, and I'm going to explain you. The problem is that you say at the start that the headers of the Python objects takes much memory. Okay, this not something new because also Java objects takes much memory because they contains a header. The problem that we want to have memory tiering in Python is that we demand more memory for applications, and if yes, what is this application that they demand a lot of memory? And also large address spaces, for example. And also, how much is the cost of the garbage collector in Python in this kind of setups? Yes, if you can tell us. Yeah.
Okay. So your concern is regarding the not with the object header, right? But the application memory. Okay.
Yeah.
So regarding that, I think we tested a lot of more than 20 actually workloads, and okay. So the thing is, I agree with you that the JVM and the CPython also both have their own object headers, right? But unfortunately, the prior works only handle. I'm talking about within a program language runtime. They only target C++ or JVM. But Python this is an untouched area. So we purely based on that one of the premises, we built this system, which only works for Python. So similar, semantics works also for JVM that they couldn't work for Python. So this is not about the header problem, but more of the the program feature enabled tiering solution. So regarding your second question about the GC overhead, right? I think as I mentioned in the previous slides, let me go back to that. Okay, so our overhead comes from the two parts, right? One is the marking overhead, which is purely original system, because the CPython itself doesn't maintain the full object scope. So that we have to pay for the price for the marking, at least for the first time. And for the second part of the overhead, it comes from the CPU additional overhead in the critical path when it's trying to increment or decrement the reference counting, because we're trying to have a MTP count separate from the original reference counting. So we note that at this project, we do not make any changes to the existing CPython GC. CPython GC has two parts, right? First part is the reference counting. When the reference count drops to 0, it is logically freed. Second part is the detect of the cyclic references. We're not changing any of this existing GC logic. So, well, yeah, does that answer your question?
No. So in a breakdown of your time, the GC, it might be the same in all in TPP, Autonuma, Memtis, MTP. But what is changed is let's say, the application thread time. Is it this part?
No. So you're talking about these slides, right? So on we show the perform better. The reason that MTP does not perform the best in terms of runtime is because of those overheads that I just explained. And for the baselines, the TPP, Autonuma, Memtis, they are all the OS-based their own overhead, but their overhead does not stem from the Python virtual machine, but stems from the OS page sampling.
Okay.
Yeah, so they're all coming from different sources. Yeah.
Okay. Thank you again for the presentation. I don't know if there is any other question. No? So
Thank you.
we can continue with the third presentation for today. So the floor is yours.
Okay, thank you. So I'll present runtime save, which is a graph database of runtime values. My colleagues from Italy. Okay, so here is the motivation. Usually, concrete runtime values of objects in some debugged programs are ephemeral. So what if we persisted them, to some persistent database on disk? So currently there are two existing approaches which are focused on this. The first one is example-based approach, but this lacks scalability. So it's not for large object graphs. It's usually just from some small objects of, I don't know, a few sub-objects, not for, I don't know, megabytes of large memory object graph. And the second approach is omniscient debugger or record and replay technique, which uses opaque storage formats, and they lack some easy queryability. You cannot easily query the saved values. So therefore, we designed runtime save, which is an approach that stores runtime values of variables collected from the Java virtual machine and some associated metadata into a Neo4j graph database. So it is basically a middle ground between these two existing approaches. It combines easy queryability using Cypher language, which is included in Neo4j, and on the other hand, it has sufficient scalability. So the number of saved nodes with respect to number of saved nodes, edges, and speed. So the first part of our approach is data collection. So imagine some program running in an IDE, and it is currently in a debugger. So the developer can choose three options how to save some objects from memory to disk. The first is manual object selection, when the developer just clicks, for example, some variable in a variables view and chooses the option like save this variable because I don't know, I like it because it's related to some bug I'm working on, so it's interesting and I want to save it on disk and maybe add some note to it. The second option is save points. Save points are an alternative to breakpoints, but instead of pausing the program as breakpoints usually do, we just save all the variables currently in scope to a database and then continue running the program. So this is the goal. The third option is sampling. Here we collect the values of variables from every nth executable source code line for the first t executions. So basically, if we set the n and t to infinity, then we have basically a full tracer or full recorder of the program. Now continue with the graph model of runtime save. We have a two-layer model inspired by Git internals. I don't know if you know how Git works by its internal working, but basically in runtime save we have hash nodes. So this is a layer of nodes with hashes assigned. This includes stack frames, objects, arrays, strings, primitives, and null. These are the nodes which are mirrored from the Java memory. So we just mirror the Java memory graph into our hash nodes. And the second layer is some layer above this one, which stores metadata related to these hash nodes. So for example, we can create some location information like class, method, line number, free text nodes, and many other possibilities. And these metadata nodes point to these hash nodes and tell us something more about, for example, this node is important because it is related to some bug, this node was collected from line number 40, and so on. So here is a specific example, specific instance of of our graph model. So we can see, I don't know, this frame node, string node, object, primitive array, which are basically just straightforward mirrors of the Java memory graph. So it's quite simple. And then we have this metadata layer up here, such as node, line, method, class, and we can see they point via edges to the hashed nodes. Each hash node again points to some other hash nodes using some relations, which are labeled by type has field with the property name of family and so on. So this basically is a representation of some object which has fields, I don't know, some stack frame which has variables, array which has elements, and so on. So this is basically stored in the database in Neo4j. It is quite straightforward. If you can think about it, it's just one-to-one mapping between JVM, there is an object graph, and this is basically the same, almost the same as the graph in Neo4j. So it's quite simple. Now, where's the catch? Why is not so simple? The problem, of course, is performance. This is totally slow. It's absolutely unusably slow. We just map this naively without thinking more about it. So we created some approaches to speed up the saving process. The first approach to speed up saving is packing. Packers are graph shape simplification transformations, which we optionally apply before storing values into database. So they first reduce data volume, which is faster, and then they also, by the way, simplify comprehension by humans. This is some byproduct. For example, a sparse array packer replaces all array nodes. So for example, this can be a node containing edges pointing to, I don't know, 1,000 nodes. So it's large array. It replaces them with just one simple node of type sparse array, which contains some metadata or some information that it has a length of 1,000 and it contains only zeros. Yes? So it is like replacing 1,000 nodes with one node, which speeds up saving. In other packers which we created are linked list packer, same primitives packer, primitive array packer, and so on. So this is an extensible approach with some domain-specific algorithms which simplify the graph to contain less nodes, less edges, and be faster and more and easier to comprehend. Now the second approach to speed up is hashing. This is focused on deduplication. Well, you can imagine that a large object graph in Java has so many duplicates. Yes, basically there are maybe, I don't know, many similar arrays of similar objects which are differing only by very small parts. So deduplication is causing faster storage, also less storage space. How do we hash these nodes? We use a content addressable system inspired by Git internals. So again, we're inspired by Git, which uses this content addressable system. It is based on Merkle trees, but again, here's the catch. We have a graph, not a tree, yes, so this is the problem. Now, what are our conditions which must be fulfilled? So first one, nodes with the same hashes are equal by deep value-based equality. So this is the main condition, main goal which we should fulfill with our hashing. So basically you can say that, okay, these two nodes have the same hash, so then absolutely they are value equal, yes? Recursively value equal, all these big graphs are equal if these two nodes have the same hashes. This is also how Git works. So we devised a custom graph hashing algorithm which has these properties, these requirements. First, hash is computed for every node, not only for the whole graph, but for every single node which has a unique hash. And we can identify each given node with this hash. Second one, we should avoid encoding which node is a root, of course, because we can point to any node in this large graph and consider it a root. So there is no one single root of the whole graph. We can select some subgraph and say, okay, so now we have this subgraph and this is now our root. The third property is that each node's hash encodes the node's labels and properties, such as, I don't know, the name of the variable and so on. Then the properties of the outgoing edges. And third, recursively the same for all reachable nodes and edges. So this hash encodes not only the node itself, but the whole subgraph which is reachable from this node. And the fourth property is that there are no hash collisions in practice. this is like in Git. If we had hash collision, there would be some data loss, yes? This is how Git works, and this is also how our approach works. It works in practice, yes? It is not in theory, but in practice, yes. So here is some specific example. We can have this one graph on the left stored in our database. These letters A to F are some specific hashes. Then we have this second graph which we want to store in our database now. You can see that many of the nodes have same hashes. Yes, this is like almost the same graph. I think that just B and C are swapped. Yes, they are absolutely the same, but B and C are swapped. So this is just the only changed. And you can see that we quite well deduplicated the graph because there are not like, I don't know, 6, 12 or so nodes. There are just, I don't know, 1, 2, 3, 4, 5, 6, 7 nodes. Yes, so there is great deduplication. We reused the existing parts of the graph, and it is saved quite well. You can see an important property here that all the relationships of reachability are preserved with our hashing. So, for example, if this A has an edge called 1 that points to C, which points via an edge called A to E, which points via an edge A to F, and so on, this reachability transition is preserved in the final graph. So we can just trace it here. A points via 1 to C, C points via A to E, E points via A to F. So this whole reachability transition is preserved absolutely in the original, from the original graph in the result. So the querying is absolutely natural. It's really like what is reachable in the origin that is reachable in the database. Okay, now again here's the problem. Some nodes have the same hash, but they are not reference equal, because we can have some specific cases when two nodes have the same hash, but they are really just copies of the same data. So we solved this by computing the ID hash of each node. The ID hash of each node encodes its hash, its copy number, which is just the device travel order, and the hashes and copy numbers of all reachable nodes transitively again. So here we can see just small example again. This is our original graph. This is our copy numbers, yes? So this is hash B copy number 1, hash B copy number 2, and copy 3. This is what we want to save into database, and this is the resulting deduplicated graph. Now, of course, the result is not totally deduplicated. This is not absolutely perfect. There are some instances which are not perfect deduplication, but it is nevertheless something reasonably well performing. Okay, now we have everything we want to save, so we can save the graphs finally into database. Now we use each ID hash of each node as a unique constraint. So we cannot have two nodes with the same ID hash in the database. This is a unique constraint. Now our graph is condensed into a directed acyclic graph, and redundant edges are removed. So we have basically some dependency graph of nodes, and we traverse this dependency graph from the root. So we first try to insert the root node, and if this root node is already present in the database, we just stop. So we have, for example, a very large graph of objects, for example, a megabyte large of objects, and we see that the root of this graph is already present in the database using this ID hashing comparison. We just stop and everything is solved. Otherwise, we continue recursively inserting the target nodes, traversing this directed acyclic graph. Again, we continue until we again find some ID hash which is already present, and then we stop. Okay, so we perform some preliminary evaluation of our approach. We tried saving all variables in scope for the first execution of each line, but that slowed down the program like 30 or 40 times. Yes, so it's really, even after the optimizations, it's really slow. So just some anecdotal evidence, it slowed down the program before these optimizations like 3,000 times. Yes, so it was unusably slow. Now it's just slow. But the main problem is really technical, because just using Java debug interface slows down the program 10 times without doing anything relevant. So this is just a technical thing. We should improve it in the future. Now we perform some other evaluation, which we focused on the number of nodes, edges, and the insertion time, but without using JDI. We just mocked it with some other approach. So now we compared a plain approach without any optimizations. We just straightforwardly mapped the Java memory graph into Neo4j database without doing anything important. Then we just used our packing, then only hashing algorithm, and then we combined both packing and hashing. And you can see that the number of nodes dramatically reduced. This is like 50 times reduced number of nodes, 20 times number reduced number of edges, and more than 10 times improvement in the insertion time into database. So this is really drastic improvement when you compare the plain approach with our packing and hashing. So this really helps with scalability. What are the applications of runtime save? We can do some querying on it. Yes, of course, we have this language called Cypher, which is great for querying graphs. We have visualization for free. We can just open many existing visualization programs and just explore our graph. We can start even a program at any line. This is our demo, which we included in the paper. Well, what is the problem with starting a program at any line in general? The problem is that we don't have local variables in scope available. Yes, every line in the program needs really some variables, some specific variables to be started, but we can easily load them from the database. We already saved them before, so now the problem is basically solved. Just load the correct variables and it's solved. There are other applications like program comprehension, API exploration, storage of some values for unit testing, use it as a team's knowledge base, software repository mining using runtime data. Yes, so you just don't do repository mining using source code, but using runtime data, using variables. Yes, so there are so many applications. You can imagine almost everything. So in conclusion, runtime save is a reasonably performant approach for saving values of Java variables using from Java variables from runtime using this Neo4j graph database. It is available as an IntelliJ plugin at this address if you want to try. And as a future work, we should replace Java debug interface with bytecode instrumentation. This is a speed up improvement, and maybe better support some data editing deletion, because now we can insert values into database, but yes, editing is quite not yet good for now. There are many other future ideas. You can find them in the papers, in the paper. Okay, so that's it, and thank you very much.
Well, thank you very much for the great talk. And do you have any question?
Well, using the garbage collector, yes.
Well, the garbage collector is traversing the heap for you, right? So you find all the objects.
Yes, it finds all the objects, but the garbage collector runs at some unpredictable times. And well, my aim is not to save just any values, some random values. I would like to save some specific values. For example, the programmer would like to save, I don't know, the first value that occurred at this line, for example, yes? Or I don't know, he would like to say save a value which is equal to 10, and if this value is equal to 10, then it saves, I don't know, these referred objects, yes? So the programmer should specify using these save points or using some manual selection or using some sampling criteria which values should be saved. So my goal is not to save any values at all, like save these values, I don't care. I should save just some specific values, yes, but if I wanted to save just any values at all, like absolutely irrelevant which one, at which time point in the execution, if it is at the beginning of the program, at the end of the program, in the middle, if that doesn't matter, then yes, it would be possible to use garbage collection.
Thank you.
Maybe I can get that clear. Every time you have a write that updates some part of an object, the hash for the object and everything that points to that object needs to change?
Yes, so every object, the hash of every object includes or encodes the hashes of all referred objects. So, for example, this.
The closure of the object, which would be half the heap.
Yes, it is really. It is really important point. This could be half a heap. If this is the case, then we just traverse half a heap and store half a heap. Yes, because there is no practical solution to this in general. But our main problem is maybe it is not the collection itself. Really, the currently which I encountered was that the bottleneck, the time bottleneck, was currently saving to database. Yes, because saving to database is I/O. It's input/output. It's really slow. It's using TCP packets and some disk access and so on. So currently, I focused on this saving part. So yes, at each point I would like to say some variable. I traverse the whole part of the heap which is relevant, and then yes, using some optimizations, I try to condense it or try to somehow simplify it to saving to simplify the saving part. Yes, so the saving part is optimized. I don't save too much data, but yes, the traversal part of the graph is not yet simplified, and I should just traverse everything that is necessary. Thank you.
A follow-up would be, if you have data structures that are immutable, which means no updates, could you do something better with the hash?
Yes, if we had only immutable data structures, then it would be really simple, because we can just see that this object didn't change during this time, so we could just assume that its hash is the same, and we shouldn't recompute its hash. So yeah, that would simplify a lot of things. Thank you.
Okay, thank you for the questions, and thank you again for the great talk.
Thank you.
I'm going to. Okay.
Okay. Oops. Oh. No. Oh my god. Just a moment. Oh my god. No. Changes? No. No. Okay, I don't use it. Yeah, okay. So, thank you. That brings us to the end of this workshop. So, I'd like to sincerely thank all speakers, session chairs, and participants for making this lively and very inspiring workshop. So, and I also say especially thanks to the SIGPLAN AV team and also student volunteers. Thanks so much. And okay, so we hope to continue this community next year, and please stay in touch through the mailing list and the other social channels. And thank you all, and enjoy the rest of Splash. Yeah.
Yeah, I also just want to very quickly thank Yuzuka for organizing. So thank you. Next year, you might know Splash is going to be in Oakland in California. So if you want to be there, send your papers to VMIL.